Have you ever looked up at the night sky, at the countless stars glittering like tiny beacons in the endless dark, and wondered, where did it all come from? Not just the stars, not just the galaxies, not even just the vast universe itself, but existence. Everything, the fabric of reality, time, space, and the laws that hold them together. This is one of the deepest questions humanity has ever asked. What was before the beginning? For centuries, human beings have tried to answer this. Ancient myths spoke of gods crafting the cosmos from chaos, of worlds emerging from primordial oceans, of cosmic eggs hatching the heavens. Philosophers debated whether the universe had always existed, or if it had been born at a specific moment in time. And then, in the last century, science gave us a profound answer. The universe as we know it began with what we now call the Big Bang. But that answer, while groundbreaking, raised even more questions. If everything began in that first instant of unimaginable heat and density, then what happened before that? Was there a before? Did time itself begin with the Big Bang? Or is there something hidden beyond that veil of cosmic origins? Something older, deeper, stranger than anything we can yet imagine? That is the journey we are about to take together. This video is not just about science. It is about wonder. It is about curiosity. It is about the human drive to reach beyond the horizon of knowledge. Over the next few hours, we will explore the history of cosmology, the science of the Big Bang, the mysteries of cosmic inflation, and the daring theories that suggest what might have existed before the universe itself. We will ask whether the cosmos might end and begin again in an eternal cycle of death and rebirth. And along the way, we will reflect on what all of this means for us, for you. Sitting here, listening, as a conscious being inside this vast and ancient universe, this is not going to be a quick explanation or a simple lecture. Instead, imagine this as a long cosmic journey, a slow unfolding of thought and imagination, the kind of story you can drift into while resting, while letting your mind wander among the stars. The question, what was before the Big Bang, may sound like a straightforward one. After all, when we ask about events in history, we naturally want to know what came before and what came after. If you ask about the birth of the Earth, we can trace it back to the formation of the solar system. If you ask about the solar system, we can trace it back to a swirling nebula of dust and gas. If you ask about the atoms in your body, we can trace them back to stars that exploded billions of years ago. Everything has a history. So surely the universe itself must have a history too, right? And yet, this is where things become complicated. Because when we talk about the Big Bang, we are not just talking about an event within time. We are talking about the origin of time itself. The Big Bang is not simply the beginning of matter and energy. It is the beginning of space and time. That means asking what happened before is not like asking what happened before you were born, or what happened before a storm arrived. It may be a question that has no meaning at all, or it may be a question that leads us to extraordinary new insights into the nature of reality. In the next 3 hours, we will walk slowly through this cosmic landscape. We will begin by exploring how humanity first came to even realize that the universe had a beginning. We will look at the birth of modern cosmology, at Einstein's equations and Hubble's observations, and at the revolutionary moment when science revealed that the universe was expanding. We will see how this led to the idea of a hot, dense beginning, the Big Bang. Then, we'll dive into one of the most fascinating theories of modern physics, cosmic inflation. We will ask how inflation might explain the structure of the universe we see today, and whether inflation itself suggests that our universe is just one bubble in a vast multiverse. From there, we will face the heart of the question, what could have existed before? We will explore bold and imaginative theorecyclic universes, bouncing cosmologies, the multiverse, string theory, quantum gravity, and more. Some of these ideas suggest that our universe is not the first nor the last, but just one chapter in an infinite story. Others suggest that the very concept of before may dissolve once we reach the deepest level of reality, and then, finally, we will turn our gaze to the future. Will the universe last forever? Could it collapse in a great crunch or tear itself apart in a big rip? Could there be another Big Bang in the far future, igniting a new cosmos? Throughout it all, we will keep circling back to the deeper, more human questions. Why does it matter? Why do we care what happened before the Big Bang? And what does it mean for us to be here in this universe, at this moment in cosmic history? So find a comfortable place. Let your mind settle. This is a journey not only of science, but of imagination. A journey that stretches across time, across space, and perhaps even beyond the universe itself. Together, let us step into the mystery of the beginning. Human beings have always been creatures of stories. Long before we had telescopes or equations, we had myths. Ancient civilizations tried to make sense of the origin of everything through imagination. The Mesopotamians told of a cosmic sea, out of which gods battled and shaped the heavens and earth. In India, the Vedic hymns spoke of a primordial being whose body was sacrificed to create the world. The Greeks imagined chaos, an empty void, giving birth to Gaia, the earth, and Uranus, the sky. In China, myths told of Pangu, a giant who cracked open the cosmic egg, separating heaven from earth, though separated by distance and culture. These myths share something powerful, the intuition that the universe must have had a beginning. That things could not simply be, they must have come into being. These stories reflect the human need to understand origins, not just of rivers or cities or dynasties, but of existence itself. And yet, for thousands of years, philosophers debated whether the universe truly needed a beginning. Some argued it must have always existed, infinite in both directions, without origin or end. Others believed it must have been created in a single act, whether by divine will or some cosmic principle. This tension between the eternal and the created is woven deep into human thought. It is a question that has haunted us since we first looked at the night sky and wondered fast forward to the last century. For most of history, science, when it even considered the cosmos, leaned toward the eternal. Even Albert Einstein, in the early 1900s, believed the universe must be static and unchanging. He modified his own equations of general relativity to force them into describing a universe that simply was. He could not imagine that the universe itself might have a birth. And yet, the evidence began to tell another story. Edwin Hubble, observing galaxies in the 1920s, discovered that the light from distant galaxies was stretched, shifted toward the red part of the spectrum. This was the sign of motion, galaxies moving away from us. The universe was expanding. This was shocking. If the universe was expanding now, then in the past it must have been smaller. Go back far enough, and everything must have been concentrated into a single, unimaginably dense point. This was the birth of the Big Bang theory. At first, many scientists resisted. Some clung to the steady-state model in which the universe had no beginning, and new matter was continually created as it expanded. Others dismissed the Big Bang as too speculative. But as decades passed, the evidence mounted. The discovery of the cosmic microwave background radiation in 1965 provided near irrefutable proof. It was the afterglow of the Big Bang itself, the faint whisper of the universe's fiery birth. But with this discovery, a new question emerged. If the universe began with the Big Bang, what came before it? This is where the paradox lies. Because the Big Bang is not like any other event. It is not a firework exploding in the night sky, where we could ask what happened before the firework was lit. It is not even like the birth of a star, where we can trace back the clouds of dust and gas that collapsed to ignite it. The Big Bang is the origin of time itself. When cosmologists speak of it, they mean the moment when not just matter and energy, but space and time itself came into existence. Asking what happened before may be like asking what is north of the North Pole. It is not that there is something hidden beyond. 'Tis that the very question might dissolve. And yet, physicists, philosophers, and dreamers are not satisfied with that. They continue to probe, to speculate, to imagine. Because maybe the Big Bang is not truly the beginning. Maybe it is just one chapter in an endless cycle. Maybe it is one bubble in a vast cosmic foam. Maybe it is a transformation, not a creation. These are the questions that will guide our journey. So how will we travel this path? We will begin with the human story, how we went from myths to mathematics, from imagination to observation. We will see how science built a picture of the universe's birth, and how each new discovery reshaped our understanding. We will then dive into the structure of the Big Bang itself. What really happened in those first few seconds? How did particles form? How did light emerge? And how did the seeds of galaxies take shape? From there, we will encounter cosmic inflation, the idea that in the tiniest fraction of a second, the universe expanded faster than light, smoothing out the cosmos and creating the structure we see today. We will ask, did inflation itself have a beginning? Or has it been going on forever, spawning countless universes? We will then stand at the edge of the known and look beyond. We will explore cyclic universes that collapse and are reborn, multiverse theories with infinite variations of reality, quantum bounce models that replace singularities with a cosmic rebound. Each of these is bold, speculative, and thrilling. We will reflect on what these possibilities mean, not just for science, but for philosophy. If the universe has no beginning, what does that say about cause and effect? If there are infinite universes, what does that mean about meaning itself? Finally, we will gaze into the future. Will our universe expand forever, growing colder and darker until nothing remains? Will it collapse into another Big Bang? Will there be, someday, another beginning after our end? This is not a story with simple answers. In fact, much of what we will discuss lies at the frontier of knowledge, where physics blurs into philosophy and science shades into speculation. But that is what makes it beautiful, because when we ask about the origin of everything, we are really asking about ourselves. How do we fit into this vast cosmos? What does it mean that we, made of stardust, can even ponder these questions? And why, in a universe so immense, do we long for a sense of beginning? So, as you listen, let your imagination drift. Picture the birth of stars, the dance of galaxies, the silent unfolding of time itself. Imagine cycles of universes, multiverses without end, quantum fields bubbling with creation. Let the questions guide you, not toward certainty, but toward wonder. Because perhaps the greatest gift of cosmology is not in the answers it gives, but in the awe it inspires. So welcome. Welcome to this journey beyond the beginning. Welcome to the story of the Big Bang, of what may have come before, and of what may come after. Settle in, relax, open your mind. We are about to step into the greatest mystery of all, the mystery of existence itself. From the earliest flickers of human thought, one question has lingered like a shadow over our imagination. Where did everything come from? Long before the tools of science, long before telescopes or particle accelerators, people looked to the heavens and wondered. The stars were mysteries, the sky itself a canvas of questions. And the origin of it all demanded an answer. And so humanity invented stories, grand, sweeping, poetic myths that sought to explain the birth of the cosmos. These stories were not just tales for entertainment. They were survival. They gave meaning to existence, a framework for understanding our place in a vast and uncertain world. In Mesopotamia, one of the earliest cradles of civilization, the story of creation was told through the Enuma Elish, In this ancient Babylonian myth, the world began in a formless ocean, where two primal beings, Apsu, the fresh water, and Tiamat, the salt sea, mingled in the void. From their union came younger gods, whose battles shook the cosmos. In the end, the storm god Marduk defeated Tiamat, split her body in two, and from one half made the heavens, and from the other, the earth. The universe in this vision was born from conflict and sacrifice, shaped by divine struggle. Across the world in ancient Egypt, the story shifted but echoed familiar themes. The universe was first and endless, watery chaos called none. Out of this ocean rose a mound of earth upon which the first God stood. From him light and air emerged, then the sky and the land, then all the order of the cosmos. Again, water, chaos, and transformation were at the heart of creation. In India, the Vedas, among the oldest sacred texts in human history, offered poetic riddles rather than clear answers. One hymn, the Nasadaya Sukta, begins with haunting honesty. There was neither non-existence nor existence then. There was no realm of air, no sky beyond it. It dares to ask whether even the gods know how the universe began, or whether the mystery lies beyond all comprehension. In another myth, the universe was born from the cosmic being Purusha, whose body was divided to form the world, much like Tiamat in Mesopotamia. The Greeks told of chaos, a primordial void from which Gaia, the earth, Tartarus, the underworld, and Eros, love, emerged. Chaos was not disorder, but emptiness pregnant with potential. Later, philosophers like Plato and Aristotle tried to move beyond myth into rational explanations, but even they could not resist the temptation of imagining beginnings. Plato's Timaeus spoke of a divine craftsman shaping order from disorder, while Aristotle argued for an eternal universe, uncreated and unending. Farther east, in China, the myth of Pangu described a cosmic egg that contained all things. Inside the egg, chaos swirled until Pangu awoke, splitting the shell. The light parts rose to form the heavens. The heavy parts sank to form the earth. Pangu held them apart, growing taller each day, until his death transformed his body into rivers, mountains, and stars. These stories are astonishing in their variety, and yet they reveal something universal about humanity. Across cultures and continents, people sensed that the universe was not static, it had a beginning. They looked at the world and saw evidence of birth and transformation, rivers springing from hidden sources, plants sprouting from seeds, children born from parents. It was only natural to imagine that the universe itself must have been born, too. But the myths also reveal another truth. The human mind does not easily accept nothingness. It is nearly impossible for us to imagine a true beginning from absolutely nothing. And so, in nearly every story, creation is not from nothing, but from something. Water, chaos, a void, an egg, a divine body. The universe does not appear ex nihilo, it is shaped, divided, awakened. This instinct to always begin with something has echoed through history, from myth to philosophy to science itself. As centuries passed, these myths evolved into philosophical reflections. In India, thinkers of the Upanishads speculated about a universal spirit, Brahman, that transcended all beginnings. In Greece, philosophers debated whether the universe had always existed. The question of origins became not only a story to be told, but a problem to be solved. Aristotle's idea of an eternal universe dominated Western thought for centuries. To him, the cosmos could not have a beginning because that would imply a time before time itself. Motion, cause, and existence required an eternal chain. Similarly, in many Eastern philosophies, the cosmos was seen as cyclic, eternally reborn through endless cycles of creation and destruction. Hinduism envisioned cycles of kalpas, vast ages in which universes arise and fall like breaths of the cosmic being. Buddhism too often imagined endless worlds, without a singular first cause. Meanwhile, in the Abrahamic religions, the view was different. Judaism, Christianity, and Islam each taught that the universe had a definite beginning, created by God out of nothing. In the beginning, God created the heavens and the earth. Here, the cosmos was not eternal, but contingent, dependent on divine will. This shaped centuries of thought. The idea that there was a singular creation. A starting point of time became deeply woven into the Western imagination. Thus, by the time science began to seriously confront the question of the universe's origin, it inherited a vast tapestry of myths, philosophies, and theologies. Some saw the universe as eternal, some as cyclic, some as born in a singular act. But all agreed on one thing: the question mattered. To ask where the universe came from was to ask the deepest question of all: why is there something rather than nothing? So, as we step into this journey, we must remember that we are not the first to wonder. We stand on the shoulders of countless generations who looked at the sky and imagined beginnings. Their myths may not have been scientific, but they were profound expressions of human curiosity. They remind us that the mystery of origins is not just a scientific puzzle, it is a human one. And in many ways, even with all our telescopes and equations, we are still telling stories. Our modern cosmology may be mathematical rather than mythical, but it serves the same purpose: to help us make sense of existence, to give us a narrative of beginnings, to satisfy our restless imagination. In the next section, we will watch how these stories began to transform into science, how the human longing to understand creation gave birth to cosmology, and how the first steps toward the Big Bang were taken. When humanity began shifting from storytelling to reasoning, the question of origins did not disappear, only became sharper. Philosophers sought to replace divine battles and cosmic eggs with logic, geometry, and natural principles. The universe, they believed, could be explained not through myth, but through order. In ancient Greece, this transition is striking. Thinkers such as Thales of Miletus, often called the first philosophers, suggested that water was the underlying principle of everything. To him, all of reality was reducible to one fundamental substance. While we may smile at the simplicity, his idea was revolutionary. The universe might be understood through natural causes, not divine drama. Thales' successors proposed their own primordial substances. Anaximenes suggested air, Heraclitus pointed to fire, while Anaximander spoke of the apeironth, the boundless, the infinite. These were not yet scientific theories in the modern sense, but they were daring steps away from myth and toward abstraction. They showed that humans could imagine the universe in terms of principles rather than stories. Then came the atomists Leucippus and Democritus, who argued that everything is made of tiny, indivisible particles moving in a void. Here at last was a vision that resonates uncannily with modern physics. The cosmos was eternal, without beginning, its changes explained not by gods, but by the ceaseless motion of atoms. The atomists were often ignored or dismissed in their time, but their boldness would echo centuries later in modern science. Meanwhile, Plato took a different path. In his dialogue, Timaeus, he imagined a divine craftsman, the demiurge, who shaped pre-existing matter into order, much like an artisan forming clay. Plato's cosmos was not eternal in its present form. It was organized at some point, yet it was not created from nothing either. The universe always had matter, but its structure came later. Through reason and design, Aristotle, Plato's student, rejected this. To Aristotle, the cosmos could not have a beginning because every beginning requires something before it. Time itself, he argued, must be eternal. Motion and causation stretched infinitely backward. The heavens, with their perfect circular motions, were eternal and unchanging, while the earth below was subject to change and decay. For nearly 2,000 years, Aristotle's vision dominated Western thought. The universe was eternal, orderly, and fixed. It had no beginning, because beginnings belonged only to things within the universe, not the universe itself. The Roman world inherited these ideas. And through thinkers like Lucretius, atomism survived in poetic form. In his epic De Rerum Natura on the nature of things, Lucretius described an infinite universe, filled with countless worlds born from the random collisions of atoms. He dismissed divine creation, insisting that the universe itself required no gods. For centuries, his poem was nearly forgotten. But when rediscovered during the Renaissance, it would help spark new debates about infinity and beginnings in parallel. Other traditions wrestled with the same mystery. In India, philosophy continued to expand the idea of cosmic cycles. Hindu cosmology described universes that lived for billions of years before dissolving, only to be reborn. The Mahabharata and Puranas describe time not in years, but in kalpas-fast cycles so long that human history seems like a blink. In Buddhism, the universe, too, had no ultimate beginning, but arose and passed away in countless cycles of dependent causation. Unlike the linear creation of the Abrahamic faiths, Eastern thought leaned toward infinity and recurrence. The Abrahamic religions, however, stood firm in their claim. The universe was created. In Judaism, Christianity, and Islam, creation ex nihilo, creation from nothing, became a cornerstone. Time itself had a starting point, and the cosmos was not eternal but contingent, dependent on the will of God. This belief gave rise to profound theological debates. Could something truly come from nothing? Could an infinite God exist outside time and bring time into being? By the Middle Ages, these questions shaped intellectual life. Islamic philosophers like Al-Ghazali argued passionately against the idea of an eternal universe, while thinkers such as Averroes defended Aristotle. In Christianity, St. Augustine grappled with the meaning of Genesis, concluding that time itself was created along with a universe, an idea that foreshadows modern cosmology. Augustine wrote, "There was no time before God created the world. Time itself began with the creation." This insight that time has no before would echo centuries later when cosmologists described the Big Bang as Europe entered the Renaissance. Curiosity flourished again. The rediscovery of classical texts and the birth of experimental science began to erode the dominance of Aristotle. Copernicus, Galileo, and Kepler showed that the heavens were not immutable but dynamic, governed by mathematical laws. The Earth was no longer the center of the universe. It was just one world among many. The 17th century brought Isaac Newton, whose laws of motion and gravity described the universe as a grand machine. To Newton, the cosmos was infinite and eternal, stretching endlessly in all directions. He believed that God created this machine, but that it had no beginning in time. Newton's contemporary, however, the German philosopher Leibniz, challenged this view. Leibniz asked, "Why is there something rather than nothing?" If the universe were eternal, he argued, it would still not explain its existence. There must be a sufficient reason for why the universe exists at all, and that reason, to him, was God. Newton and Leibniz represent a tension that persists today. Is the universe self-sufficient? Or does it require something beyond itself to explain its existence? By the 18th century, Enlightenment thinkers pushed further. Some embraced deism, imagining a God who created the universe but did not intervene thereafter. Others, like the French materialists, leaned toward an eternal, self-existent cosmos. The question of origins remained open, suspended between science and philosophy. Faith and reason by the 19th century. Science began to confront evidence that the universe might not be eternal after all. Thermodynamics introduced the concept of entropy, the tendency of energy to disperse, of systems to run down. If the universe had existed forever, why had it not already reached complete equilibrium, a state of heat death? This hinted at a finite age. The German physicist Hermann von Helmholtz and others argued that the universe must have had a beginning in time. Otherwise, entropy would already be maximized. Philosophers seized on this. If the cosmos was winding down, it must have been wound up at some point. But when and how? By the turn of the 20th century, the stage was set. Myth had given way to philosophy, philosophy had given way to science, and science was about to take its boldest step yet. With Einstein's theory of relativity, Hubble's discovery of an expanding universe, and the birth of the Big Bang Theory, humanity was on the brink of a radical reimagining. The universe had not always been here. It had a beginning. So in this arc, from myth to philosophy to proto-science, we see a remarkable continuity. The questions of Thales, Aristotle, Augustine, and Newton are not so different from ours. They all wrestled with the same paradox. Could the universe really have come from nothing? Or has it always been? And just as myths once gave shape to wonder, philosophy and early science gave us the intellectual tools to even ask the question clearly. Without them, the Big Bang would not have been imaginable. The mystery of origins was never solved in these eras, but it was refined, clarified, sharpened. The question was prepared, waiting for modern cosmology to attempt an answer. From the stories told around ancient fires to the libraries of classical philosophers, the question of origins was never truly settled. Each generation inherited answers that felt incomplete, and so they asked again. This recursive cycle of questioning is, in itself, a profound statement about humanity. We do not simply accept that we exist, we demand to know why and how. And within that demand lies the seed of both science and spirituality. As philosophy matured in Greece, India, and China, we begin to see patterns that foreshadow later scientific thought. The Greek atomists, for example, suggested that all matter is composed of tiny, indivisible particles, atoms drifting in an infinite void. Democritus believed that the universe had no true beginning, that atoms simply always existed and combined in endless patterns. To him, the cosmos was eternal, without origin, without end. Meanwhile, other philosophers, like Plato, proposed a universe shaped by a divine craftsman, the demiurge, who imposed order on primordial chaos. Aristotle argued that motion must always be explained by something prior, eventually leading him to the concept of a prime mover, an eternal source of motion that itself was unmoved. In India, Vedic cosmology often spoke of a cyclical universe, endlessly created and destroyed in vast epochs. The concept of kalpas envisioned cosmic days and nights of Brahma, each spanning billions of years. A vision uncannily close to the scale modern cosmology considers. In China, Taoist thinkers describe the universe as arising spontaneously from the Tao, the ineffable way or source that cannot be named, a principle more than a being. In each case, we find a profound recognition: the universe, whether born from chaos, cycles, or ineffable voids, carries with it a mystery that seems beyond complete human grasp. This awareness that we stand before a question larger than form? No, larger than ourselves shaped not only philosophy, but also culture. Origin myths were not merely explanations, but also foundations of identity. To know where you come from is, in a sense, to know who you are. The Babylonians saw themselves as inheritors of divine victory, the Greeks as children of chaotic necessity, the Hindus as participants in eternal cycles, the Hebrews as chosen witnesses of divine creation. Our answers to the question of beginnings always reflected back upon ourselves. As centuries passed, one particular struggle became central. Should we imagine the universe as eternal or as having a beginning? This debate stretched across cultures. Aristotle's eternal cosmos clashed with the biblical notion of creation. Medieval scholars wrestled with reconciling these views, often arguing not only about theology, but also about logic. Could an infinite past exist, or must time itself have a starting point? Could an eternal universe be compatible with the Creator? Questions like these occupied the minds of Islamic scholars like Al-Farabi, Avicenna, and Al-Ghazali, who debated whether the universe could be both eternal and dependent on God. What is remarkable is how persistent this tension is, echoing even into modern science. The idea of a universe with a definite beginning versus one that stretches infinitely in time reemerges in our cosmological models. The Big Bang versus steady state, inflationary universes versus cyclic ones. Long before telescopes, humans already framed the essential choices that science would later test with data. But the real turning point came with the gradual realization that myths and philosophy, while profound, could only go so far without observation. The seeds of empirical science were planted in the recognition that we needed not only stories, but also evidence. The stars themselves became the oldest library we could read. From Babylonian records of planetary movements to Greek attempts at geometrical astronomy, humanity's attention began shifting from the imagination of origins to the measurement of reality. This did not mean myth was discarded. On the contrary, myth provided the framework of curiosity, the drive to explain. Without myth's imaginative leap that the universe has an order, a pattern, a story science might never have emerged. What changed was the method. Instead of relying only on inherited tales or abstract speculation, humans began testing, observing, and revising their views. A universe of mystery slowly became a universe of discovery, and yet the mystery never vanished. Even as philosophy gave way to natural philosophy, and natural philosophy matured into science, the question remained hauntingly open. Why is there something rather than nothing? Even now, cosmology cannot fully answer that. In fact, every discovery seems to push the question further back. If the Big Bang began the universe, what set the conditions for the Big Bang? If inflation expanded space, what allowed inflation to occur? If quantum mechanics underlies reality, what gave rise to the quantum laws themselves? We are always at the edge of knowledge, peering into the unknown. In that sense, we are not so different from our ancestors around the fire, telling stories of gods and dragons and voids. Their myths and our theories serve the same human hunger. To connect ourselves to the beginning as we close this first chapter of our exploration, we see how deeply human the question of origins truly is. From the earliest myths of chaos and creation, through the philosophies of eternity and first causes, to the birth of observational science, every stage of thought reveals the same underlying impulse. We cannot resist asking where it all began. Perhaps, in a way, the question itself is part of the answer. Our universe gave rise to beings who wonder about the universe. Out of the silence of space, consciousness emerged to speak, to question, to imagine. The cosmos in us seeks to understand itself, and so as we step into the next stage of our journey, the rise of modern cosmology, we carry with us the weight of millennia of wondering. The myths may no longer be our explanations, but they remain our companions, whispering that origins are never simple, and that every beginning carries with it the infinite shadow of mystery. For most of human history, the night sky seemed eternal and unchanging. The stars twinkled above, the constellations returned each season, and the great arc of the Milky Way stretched across the heavens with a sense of permanence. Civilizations took this apparent constancy as a sign that the universe itself was fixed, perhaps eternal. Even in the age of Galileo and Newton, the universe was often imagined as infinite, static, and unaltered by time. Newton's laws of motion and universal gravitation allowed scientists to predict the paths of planets and comets. But they also raised difficult questions. If gravity is always attractive, why doesn't the entire universe collapse in on itself? To Newton, the answer seemed to be divine balance. God had arranged the stars in such a way that stability was maintained. For centuries, this was enough. But as the 20th century dawned, new tools and new theories began to crack this picture of permanence. In 1915, Albert Einstein presented his general theory of relativity, a radical reformulation of space, time, and gravity. Gravity was no longer a mysterious force acting at a distance, as Newton had described. Instead, it was the curvature of space-time itself, shaped by the presence of matter and energy. Planets orbited the sun not because of an invisible force pulling them, but because the sun bent space-time around it, and the planets followed the curves of that geometry. Einstein's equations were breathtaking in their elegance, but they also carried unsettling implications. If matter curves space and time, then the distribution of matter in the universe should affect the overall shape and evolution of the cosmos itself. In other words, relativity suggested that the universe could not remain perfectly static. It should either be expanding or contracting. Einstein found this conclusion unacceptable. Like nearly everyone else of his time, he assumed the universe was eternal and unchanging. To force his equations to allow a static cosmos, he introduced what he called the cosmological constant, a mathematical term that counterbalanced gravity and held the universe in place. Later, Einstein would famously refer to this adjustment as the biggest blunder of his career, though in hindsight, it was more prescient than he realized. While Einstein sought stability in his equations, astronomers were collecting observations that told a different story. The early 20th century was a golden age of telescopic discovery. Advances in photography allowed astronomers to capture fainter and more distant objects than ever before. Among those leading the way was Edwin Hubble, working at the Mount Wilson Observatory in California. Using the powerful 100-inch Hooker telescope, Hubble turned his gaze toward faint nebulae patches of light that many astronomers assumed were simply gas clouds within the Milky Way. But were they? The debate raged fiercely. Some believed that these nebulae were island universes, galaxies beyond our own, while others thought they were local clouds of dust and gas. The scale of the universe itself was in question. In 1923, Hubble found the answer by identifying Cepheid variable stars in the Andromeda Nebula. Cepheids have a predictable relationship between their brightness and their period of variability, allowing astronomers to calculate their distance. Hubble's measurements showed that Andromeda was far outside the bounds of the Milky Way. The universe was far larger than anyone had imagined. This revelation was staggering. But Hubble's most profound discovery was yet to come. By analyzing the light from distant galaxies, Hubble noticed that their spectral lines were shifted toward the red end of the spectrum, a sign that they were moving away from us. Moreover, the farther away a galaxy was, the faster it seemed to recede. This relationship, now known as Hubble's law, pointed to an extraordinary conclusion. The universe itself was expanding. Space was not static, it was stretching, carrying galaxies apart like raisins in a rising loaf of bread. The impact of this discovery cannot be overstated. The assumption of an eternal, unchanging universe had dominated human thought for millennia. Suddenly, the evidence suggested that the universe had a dynamic history. If it is expanding now, then in the past it must have been smaller, denser, hotter. Follow that logic far enough back, and one arrives at a moment when everything was compressed into an unimaginably dense state. The seeds of the Big Bang Theory were being planted. Yet at the time, not everyone was convinced. Einstein himself resisted the idea of an expanding cosmos. The Belgian priest and physicist Georges Lemaître proposed in 1931 that the universe began with what he called a primeval atom, a kind of cosmic egg that exploded to form the expanding universe we see today. His ideas were bold, but they were met with skepticism. Many scientists preferred to think of the redshift as something other than expansion. Some suggested that light simply lost energy over vast distances, a hypothesis known as the tired light theory. Others clung to the possibility of a static universe held together by yet unknown forces. Still, the weight of evidence was shifting. Observations continued to confirm Hubble's findings. And relativity provided a solid mathematical framework for an expanding cosmos. Step by step, the static universe of Newton and Aristotle was giving way to a universe alive with history, change, and origin. This was the birth of modern cosmology. For the first time, humans were not merely speculating about beginnings through myth or philosophy. They were uncovering empirical, theory, evidence that the universe had a past and, perhaps, a beginning. The philosophical debate between an eternal cosmos and a created one had leaped into the realm of scientific investigation, and yet, even in this moment of transformation, mysteries abounded. If the universe is expanding, what caused it to begin expanding in the first place? What was its initial state? Could relativity describe the earliest moments of creation, or would something beyond Einstein's equations be required? The door to modern cosmology had opened, but behind it lay questions as vast as the universe itself. The discovery of an expanding universe did not immediately sweep the scientific world. In fact, it was met with hesitation, resistance, and sometimes outright rejection. Science is often imagined as a smooth march of progress, but in reality, it advances through debates, doubts, and the courage of individuals willing to follow evidence even when it overturns deeply held beliefs. Albert Einstein, despite the revolutionary nature of his general theory of relativity, was among the skeptics. When confronted with the idea of an expanding cosmos, he famously quipped that Lemaitre's primeval atom was abominable. Einstein preferred the comfort, of a universe that had always been. The notion of a beginning smacked too much of theology, and Einstein was wary of anything that resembled religious creation stories. Ironically, it was Georges Lemaitre, a Catholic priest as well as a trained physicist, who proposed the boldest cosmological vision of them all. Lemaitre's insight came from taking Einstein's equations seriously. If space and time themselves were dynamic, then rewinding the cosmic film should lead back to a singular state of unimaginable density and heat. He described this as a cosmic egg exploding at the moment of creation. Unlike myth, his idea was grounded in mathematics and observation, yet it carried an almost poetic resonance. To many, it seemed too radical. To others, it seemed too theological, too close to the language of Genesis. In the 1940s, a competing theory emerged that attempted to preserve the eternal universe, the steady-state theory, developed by Hermann Bondi, Thomas Gold, and Fred Hoyle. According to this model, the universe was indeed expanding, but as galaxies moved apart, new matter was continuously created to fill the gaps, maintaining a constant density. In this way, the cosmos had no true beginning or end, looked the same at all times and places. Hoyle, who coined the term Big Bang, somewhat mockingly during a 1949 BBC radio broadcast, became one of the most prominent defenders of the steady state. The Big Bang, at this stage, remained an idea without decisive evidence. Redshift measurements confirmed expansion, but they did not reveal the universe's earliest conditions. Could the cosmos have had a definite starting point, or was expansion simply a feature of an eternal process? The debate raged throughout the mid-20th century, dividing astronomers and physicists. What tipped the balance was the gradual accumulation of predictions. Big Bang cosmology suggested that the universe should be suffused with faint radiation, the leftover glow of its hot, dense beginning. This cosmic afterglow would be cooled by expansion to just a few degrees above absolute zero. The steady-state theory, by contrast, offered no such expectation. For years, the idea of detecting such relic radiation seemed impossible. Yet in 1965, by accident, Arno Penzias and Robert Wilson at Bell Labs stumbled upon a mysterious background noise in their radio antenna. No matter where they pointed the instrument, the signal remained. Unbeknownst to them, just across town, a group at Princeton University led by Robert Dick was preparing to search for precisely this radiation. When the two groups compared notes, the realization struck. The cosmic microwave background (CMB) had been discovered. This single finding dramatically reshaped the landscape of cosmology. Suddenly, the Big Bang Theory had a clear, testable prediction confirmed by observation. The steady-state model, elegant in its philosophical simplicity, could not account for the CMB. One by one, scientists shifted toward the Big Bang as the dominant paradigm. The idea that the universe had a hot, dense beginning became mainstream science. But even as evidence mounted, questions remained. What exactly happened at the moment of the Big Bang? Was it truly the beginning of everything, or simply the beginning of our observable universe? Could Einstein's equations, which break down at singularities, really describe the first instant of creation? The very success of the Big Bang model raised deeper mysteries. This was the paradox of progress. Every answer revealed new questions. If the cosmos expanded from a dense state, why did it expand so smoothly? Why did matter clump into galaxies rather than spread evenly? Why was the universe so uniform in temperature across vast distances? These puzzles would give rise to the next great breakthrough in cosmology cosmic. Inflation. Yet before inflation could enter the stage, cosmology had to pass through a period of maturation. In the decades after the discovery of the CMB, astronomers refined measurements of the universe's age, composition, and structure. They mapped galaxies, studied quasars, and peered deeper into space than ever before. Each discovery reinforced the picture of a universe with a dynamic, evolving history. What once seemed eternal now revealed itself as fragile, contingent, and astonishingly young on cosmic scales, just under 14 billion years old. It is striking to consider how quickly this revolution unfolded. At the dawn of the 20th century, many scientists still debated whether the Milky Way was the entire universe. By mid-century, humanity knew that not only were there countless galaxies, but that they were all rushing apart in the wake of a primordial explosion. In less than a human lifetime, our cosmic perspective expanded from local to truly universal. The transition was not only scientific, but existential. To live in a static universe was to live in an eternal stage, unchanging, indifferent to time. To live in an expanding universe was to recognize that we inhabit a storia cosmic narrative with a beginning, a past, and a potential future. Cosmology was no longer about eternal truths, but about history, evolution, and the fragile beauty of beginnings. As this new vision took root, the question of origins once again deepened. If the universe has a beginning, what came before? Science had displaced myth, but it had not erased mystery. In fact, by showing that time and space themselves might have emerged from the Big Bang, it suggested that our very language of before may no longer apply. We were at the edge of understanding, gazing into the frontier where physics, philosophy, and imagination converge. When Arno Penzias and Robert Wilson first heard the faint hiss in their radio receiver in 1965, they thought it was interference. They cleaned pigeon droppings out of the antenna, checked the electronics, and adjusted their instruments. Nothing removed the signal. That background noise, stubborn and ever-present, turned out to be one of the greatest scientific discoveries of the 20th century. The fossil light of the early universe. The cosmic microwave background (CMB) was exactly what Big Bang cosmology had predicted. The cooled remnant of radiation from the hot, dense beginning of the universe. At the time of its release, the universe was about 380,000 years old. Prior to that, matter and radiation were so tightly coupled that the cosmos was opaque, a glowing fog of plasma. As it expanded and cooled, protons and electrons combined to form neutral atoms, allowing light to travel freely for the first time. That light, stretched by billions of years of expansion, now arrives as microwave radiation. It is, quite literally, the oldest picture we have of the universe. The discovery of the CMB silenced most remaining opposition to the Big Bang model. The steady-state theory collapsed under its weight. And even Einstein's long-abandoned idea of a static cosmos faded into history. The universe had not always been as it is. It had a hot, fiery youth, and it bore the scars of that youth in the form of a faint, uniform glow across the sky. Yet the very uniformity of the CMB presented new puzzles. When scientists first mapped the background radiation, they found it astonishingly smooth. No matter which direction they looked, the temperature was nearly the same, differing only by tiny fractions of a degree. This raised what came to be known as the horizon problem. Regions of the universe on opposite sides of the sky had never been in causal contact. There had been no time for light or information to travel between them. How then could they share such a precise temperature? Another enigma was the flatness problem. General relativity allows for many possible geometries of the universe: open, close, or flat depending on the density of matter and energy. But measurements showed that the cosmos was extraordinarily close to flat, requiring conditions at the Big Bang to have been fine-tuned to an almost unimaginable degree. Why should the universe have begun in such a delicate balance? Finally, there was the monopole problem. Grand unified theories of particle physics predicted the existence of magnetic monopoles, exotic particles that should have been produced in abundance in the early universe, yet none had been observed. If the Big Bang was simply extrapolated backward with no additional mechanism, these relics should clutter the cosmos. Their absence demanded explanation. These problems signaled that while the Big Bang theory explained much, it was incomplete. The model described the evolution of the universe from a hot, dense state, but it did not explain why that state had the properties it did. The stage was set for another conceptual leap. In the early 1980s, a young physicist named Alan Guth proposed a daring idea known as cosmic inflation. Guth suggested that in the earliest fraction of a second, the universe underwent a period of exponential expansion, growing unimaginably fast, far faster than the speed of light, though not violating relativity because it was space itself that expanded. This inflationary phase could iron out irregularities, solve the horizon and flatness problems, and dilute any unwanted relics like magnetic monopoles. What emerged from inflation was a universe smoothed, stretched, and primed for the hot Big Bang phase that followed. Inflation was not just a patch on the Big Bang, it was a radical extension. It transformed cosmology from a story of beginnings into a story of processes. The universe did not simply explode into being. It evolved through phases, guided by quantum fields and fundamental forces. Guth's idea was refined by others, including Andre Linde, who proposed versions of inflation that could naturally continue eternally, spawning countless bubble universes. With inflation, cosmology expanded its scope from explaining our cosmos to speculating about an entire multiverse. The discovery of the CMB also opened the door to precision cosmology. Over the decades, satellites such as COBE, WMAP, and Planck mapped the background radiation with extraordinary detail. What had once appeared uniform now revealed tiny fluctuations, minute variations in temperature that corresponded to the seeds of galaxies. These ripples, imprinted by quantum fluctuations during inflation, were stretched to cosmic scales, later forming the large-scale structure of the universe. With these measurements, cosmology became a data-driven science. No longer was it a playground of speculation. The universe's age, composition, and geometry could be measured with remarkable accuracy. We now know that the cosmos is about 13.8 billion years old, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These discoveries gave cosmology a precision rivaling that of particle physics or chemistry. And yet, precision did not remove mystery. If anything, it deepened it. Dark matter and dark energy, which together make up 95% of the universe, remain enigmatic. Inflation, while elegant, raises questions of its own. What drove it? What ended it? And could it be tested directly? The discovery of the CMB answered the question of whether the universe had a hot, dense beginning. But it raised countless new questions about what shaped that beginning and what might have preceded it. By the end of the 20th century, cosmology had transformed beyond recognition. What began as philosophical speculation about eternal stars had become a scientific narrative of origins. Backed by observation, mathematics, and experiment, the universe was revealed to be dynamic, evolving, and astonishingly knowable. Yet with each discovery, the frontier of the unknown advanced further outward. This is the paradox of cosmology. The more we learn, the more we realize how much remains hidden. The birth of modern cosmology did not close the question of origins, it opened it wider than ever before. With inflation on the horizon, science was preparing to tackle the most profound question of all, not just how the universe began, but whether beginning itself is even the right word to use. When we hear the phrase, the Big Bang, it immediately conjures an image of a sudden, fiery explosion that birthed the universe. For many people, it feels like a cosmic fireworks show, matter and energy bursting forth from some singular point into an infinite void. But the truth is far more subtle, more complex, and far more mysterious. The Big Bang was not an explosion in space. It was the expansion of space itself. To truly understand what the Big Bang means, we need to step back and think carefully about the framework of space and time. Imagine you are holding a balloon. On the surface of the balloon, you draw a set of tiny dots. These dots represent galaxies. At first, when the balloon is deflated, all the dots are close to one another. Now imagine inflating the balloon. As it expands, the surface stretches, and the dots move farther and farther apart. Notice something important. The galaxies themselves don't expand, but the space between them grows. This balloon analogy is one of the most useful ways to picture the Big Bang. The galaxies are not flying apart into some pre-existing emptiness. Instead, the fabric of space itself is stretching. In our universe, three-dimensional space, along with time, began expanding about 13.8 billion years ago. Every galaxy is embedded within this stretching fabric, carried along by its growth. There is no center, no edge, and no preferred location. Every point of the universe is part of this grand expansion. Now, you might ask, what evidence do we have that the universe began in such a way? The first clue came from the simple observation that galaxies are receding from us. Edwin Hubble's groundbreaking work in the 1920s showed that the farther away a galaxy is, the faster it seems to move away. This relationship, called Hubble's law, revealed that the universe is not static but expanding. If it is expanding today, then logically, in the past, it must have been smaller, denser, and hotter. Rewind far enough, and you reach an unimaginably compact and energetic state, the seed of what we now call the Big Bang. But expansion alone does not tell the full story. Another vital piece of evidence came from the faint afterglow that permeates the entire universe. The cosmic microwave background, or CMB, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. This radiation is essentially the leftover heat from the universe's fiery beginnings. Today, it has cooled to just 2.7 Kelvin above absolute zero, invisible to our eyes but detectable by radio telescopes. The CMB provides a snapshot of the universe just 380,000 years after the Big Bang, when matter cooled enough for light to travel freely through space. It is, in many ways, the baby picture of the cosmos. confirming that the universe was once hot, dense, and uniform, with tiny fluctuations that would eventually grow into galaxies and stars. Equally compelling is the evidence hidden in the very atoms around us. According to Big Bang nucleosynthesis, in the first few minutes after the Big Bang, the universe was so hot that nuclear reactions fused protons and neutrons into the lightest elements, hydrogen, helium, and small traces of lithium. The predicted ratios of these elements, about 75% hydrogen, 25% helium, and a sprinkling of lithium, match astonishingly well with what astronomers observe in the oldest stars. This cosmic chemistry provides a powerful fingerprint, further validating the Big Bang model. And yet, the Big Bang theory is not about the origin of the universe in the deepest sense. It does not tell us what banged or why it happened at all. Instead, it describes how the universe evolved from an extremely hot, dense state to the vast, structured cosmos we see today. The theory gives us a timeline, a framework, and testable predictions. But it leaves us with profound questions. What triggered the expansion? What was the nature of that dense beginning? Was there something before it? Or is before a meaningless concept when time itself was born in the event? One of the most profound misunderstandings about the Big Bang is to think of it as an explosion that happened at a location in space. That picture, while intuitive, is misleading. If we return to the balloon analogy, imagine asking where on the surface did the expansion begin? The answer is nowhere and everywhere. The expansion occurs uniformly across the surface. Similarly, the Big Bang happened everywhere in the universe at once. There is no central point where it all started and no external space into which it expanded. The universe is not growing into something. Rather, the something is the universe itself. We also need to distinguish between the observable universe and the universe as a whole. Because light travels at a finite speed, and because the universe has a finite age, there is a limit to how far we can see, about 46 billion light-years in every direction. This sphere defines the observable universe. Beyond that horizon, the universe almost certainly continues, but we cannot access it. The Big Bang theory applies to the observable portion we can test and study. Whether the entire cosmos is finite or infinite remains one of the great mysteries of modern science. Another important aspect of the Big Bang is that it unfolded in stages. In the earliest fractions of a second, the universe passed through phases that defy ordinary imagination. In what is known as the Planck era, the first y-43 seconds, all the fundamental forces of nature may have been unified, governed by a quantum theory of gravity we do not yet possess. Then came the era of grand unification, followed by a burst of exponential growth known as cosmic inflation. During this brief but extraordinary phase, the universe expanded faster than the speed of light, smoothing out irregularities and setting the stage for the cosmos we know. After inflation ended, particles formed, cooled, and eventually assembled into atoms, stars, and galaxies. Each of these stages adds texture and richness to the Big Bang narrative. Far from being a single, instantaneous event, it was a process, a cosmic unfolding, with physics at every level dictating how energy condensed into matter and how structure emerged from simplicity. The beauty of the Big Bang theory lies in its ability to connect deep mathematical laws with the grandest phenomena we observe, from the glow of the CMB to the distribution of galaxies across the sky. And yet, for all its success, the Big Bang is not the final word. It is, in a sense, the beginning of our story, but not the end of inquiry. Cosmologists continue to push back the frontier, searching for clues about what might have preceded it, or whether the universe undergoes cycles of birth and death, expansion and contraction. In exploring these questions, we stretch the limits of physics, philosophy, and imagination alike. While the Big Bang theory brilliantly explains the expansion of the universe, the relic radiation, and the abundance of light elements, it leaves some fundamental questions unanswered. By the late 1970s and early 1980s, cosmologists realized that there were subtle but profound puzzles hidden within the cosmic framework. The first is the horizon problem. Observations of the cosmic microwave background (CMB) reveal that the universe is astonishingly uniform in temperature. Every direction we look has virtually the same thermal profile, differing by only a tiny fraction of a degree. But according to classical Big Bang theory, distant regions of the universe have never been in causal contact, meaning that light or Q information could not have traveled between them to equalize temperatures. How, then, did such uniformity arise? Next is the flatness problem. The geometry of the universe depends on its density relative to a critical value. If the universe is slightly denser than this critical density, gravity would have caused it to eventually collapse. If slightly less, it would have expanded too rapidly for structure to form. Measurements suggest that the universe is extremely close to flat, implying that its initial density was fine-tuned to a degree of precision that seems almost impossible. Why should the universe have started in such a delicate state? Another puzzle concerns magnetic monopoles. Theoretical physics, particularly grand unified theories, predicted the creation of these exotic particles in the early universe. Yet none have been observed. Classical Big Bang theory offers no natural explanation for their apparent absence. Enter cosmic inflation, a revolutionary idea first proposed by Alan Guth in 1980. Inflation posits that in the first tiny fraction of a second, seconds after the Big Bang, the universe underwent a brief period of exponential expansion. Space itself stretched at a rate far faster than the speed of light, inflating microscopic quantum fluctuations into cosmic scales. This rapid expansion explains the horizon problem. Regions now widely separated were once in close contact, allowing temperatures and densities to even out. Inflation also addresses the flatness problem. Exponential expansion drives the universe toward spatial flatness, smoothing out any curvature that might have existed initially. It is as if the universe were stretched like a balloon to such an extreme that any initial imperfections became imperceptible. Moreover, A18 provides a solution to the monopole problem. As the universe inflates, the density of any exotic relic particles is diluted to near zero, explaining why we do not observe them today. In one elegant stroke, inflation solved three major theoretical challenges that classical Big Bang cosmology could not address. The implications of inflation are profound. It introduces quantum physics into cosmology in a fundamental way. The tiny fluctuations in density and energy during inflation were amplified as space expanded. And these fluctuations later became the seeds of galaxies and clusters of galaxies. The irregularities imprinted on the CMB are direct evidence of these primordial quantum perturbations. In essence, the large-scale structure of the universe, galaxies, clusters, and voids owes its existence to quantum jitters during inflation. Inflation also raises tantalizing possibilities about the nature of reality itself. Some versions of inflation suggest that it could be eternal, producing a multiverse of bubble universes. In this scenario, our observable universe is just one region among countless others, each potentially governed by different physical constants and laws. The universe becomes far grander and stranger than Ruby, then Ruby, then Ruby. My only lipstick, Ruby Kiss. Ruby Kiss, only Ruby Kiss. Only Ruby Kiss has the luxurious Ruby Kiss. Has Rewixter. And Rewixt us, Ronly at least. Anything envisioned in the early 20th century, observational evidence continues to support the inflationary picture. Satellite missions like WMAP and Planck have mapped the CMB in exquisite detail, revealing patterns consistent with predictions from inflation. Tiny temperature variations, only millionths of a degree, match what would be expected if quantum fluctuations were stretched to cosmic scales during a period of rapid expansion. while direct evidence for inflation is still a subject of ongoing research. The theory has transformed our understanding of the earliest moments of the cosmos. Inflation does not replace the Big Bang. It extends it. The Big Bang describes the evolution of the universe from a hot, dense state onward, while inflation explains how that state came to be smooth, flat, and structured. Together, they form a coherent framework that answers deep questions about the origin of the observable universe, while still leaving space for wonder and mystery. Even with inflation included, profound questions remain. What triggered inflation? What energy field drove it? Could there have been something before inflation? Or is that question meaningless in a framework where time itself emerges from cosmic processes? These questions push cosmology to the edge of human knowledge, where physics, mathematics, and philosophy intersect. In the decades since the development of inflation, cosmologists have refined the Big Bang framework into what is now called the Lambda CDM model, or the Standard Model of Cosmology. It incorporates dark energy, represented by the cosmological constant lambda, and cold dark matter, CDM, explaining not only the early universe, but also its accelerated expansion today. The combination of Big Bang cosmology with inflation, dark matter, and dark energy has produced a remarkably predictive theory, consistent with observations ranging from the formation of the first atoms to the clustering of galaxies, across billions of light-years. Yet, despite its successes, the Big Bang remains a doorway rather than a conclusion. It is a framework for understanding how the universe evolved, but it hints at deeper mysteries: the origin of time and space, the fate of the cosmos, and the possibility of realms beyond our observation. As we explore these questions, we see that the Big Bang is not merely a scientific model. It is an invitation to contemplate the ultimate story of existence itself. After the first few minutes of the Big Bang and the brief but transformative period of inflation, the universe continued to evolve in ways both dramatic and gradual. By the time the universe was a few 100,000 years old, matter had cooled enough to form neutral atoms. This moment, known as recombination, allowed photons to travel freely, producing the cosmic microwave background we observe today. But recombination was only the beginning of a longer, more intricate story, the story of structure formation. Initially, the universe was nearly homogeneous, almost perfectly smooth. Yet, tiny variations in density seeded during inflation created regions slightly denser than their surroundings. Gravity began its slow, inexorable work. These overdense regions attracted more matter, gradually growing into the cosmic structures we see today. Over hundreds of millions of years, these fluctuations led to the formation of the first stars, often called population 3 stars. These stars were massive, short-lived, and crucial. Their fusion processes created heavier elements, which were later released into the interstellar medium during supernova explosions. The enrichment of the cosmos with heavier elements set the stage for planets, chemistry, and eventually life. The first galaxies formed as these stars clustered together under gravity's pull, giving rise to a universe that was no longer smooth and featureless, but rich with complexity. Galaxies merged, grew, and evolved, forming clusters and superclusters interconnected in vast cosmic webs. Each galaxy became a miniature laboratory of astrophysics, hosting countless stars, planets, and nebulae. Meanwhile, the universe's expansion continued. About 9 billion years after the Big Bang, observations revealed a surprising twist. The expansion is accelerating. This discovery, made in the late 1990s through measurements of distant supernova, led to the postulation of dark energy, an invisible force driving galaxies apart at ever-increasing speeds. Today, dark energy dominates the energy budget of the universe, accounting for roughly 68% of its total content. Its nature remains one of the most profound mysteries in modern science. Even as we observe galaxies billions of light years away, we are looking back in time. Light from these distant objects traveled across the cosmos for billions of years before reaching us, allowing astronomers to piece together a timeline of cosmic evolution. From the hot plasma of the early universe to the intricate tapestry of galaxies today. The Big Bang Theory, extended by inflation and complemented by dark matter and dark energy, provides a coherent narrative of cosmic history. Yet questions remain. What will be the ultimate fate of the universe? Will it continue to expand forever, gradually cooling until stars burn out, leaving a cold, dark cosmos? Or will some unforeseen mechanism reverse the expansion, leading to a big crunch? Current evidence suggests that accelerated expansion will continue, leading to a vast, increasingly isolated universe, where galaxies recede beyond the observable horizon and the night sky becomes emptier over trillions of years. The Big Bang also invites us to consider deeper philosophical questions. If time and space themselves emerged from the Big Bang, what does before mean? Can there be a cause for a beginning of time, or is the question itself meaningless? These questions straddle the boundary between physics and metaphysics, reminding us that the story of the universe is both scientific and profoundly existential. Despite the mysteries, the Big Bang remains a triumph of human understanding. From a few theoretical insights in the 1920s to precise measurements of the CMB, elemental abundances, and galactic structures, we have traced the evolution of the universe from its earliest observable moments to the vast cosmos around us. Each discovery has revealed more about our origins and our place in the grand scheme of existence. The theory also underscores a remarkable lesson: the universe is intelligible. By observing light from distant galaxies, measuring the faint glow of ancient radiation, and applying the laws of physics, we can reconstruct events that occurred nearly 14 billion years ago. The Big Bang Theory demonstrates that, even on the grandest scales, nature is comprehensible and its story accessible to human curiosity. Finally, contemplating the Big Bang invites reflection on the nature of existence itself. We are children of the cosmos, forged from atoms created in stars and scattered across the universe by processes set in motion at the dawn of time. Understanding the Big Bang is not merely an academic exercise. It is an exploration of our roots, a connection to the universe that makes us both infinitesimal and integral, fleeting and eternal, as we stand beneath the night sky, tracing the paths of distant galaxies. We participate in a narrative that began in a fireball of unimaginable density and temperature, the Big Bang. Theory gives us a framework for understanding that journey, a framework that bridges the earliest moments of cosmic history to the universe we inhabit today, and points toward the mysteries that still lie beyond our observational reach. Cosmic inflation is one of the most profound and transformative ideas in modern cosmology. First proposed by Alan Guth in 1980, it addresses fundamental puzzles left unresolved by the classical Big Bang Theory. Inflation suggests that the universe, in its earliest moments, expanded exponentially, far faster than the speed of light, stretching space itself in ways that transformed the very structure of reality too. Understand why inflation was needed. We must consider the problems that emerged as cosmologists studied the universe's earliest light and matter distribution. Observations of the cosmic microwave background (CMB) revealed an astonishingly uniform temperature across the sky. Different regions of space, separated by billions of light-years, seem to share the same thermal conditions. Yet, according to classical Big Bang theory, these regions could never have communicated with each other. Light had not had enough time to travel between them. This discrepancy is known as the horizon problem. Similarly, perplexing was the flatness problem. The universe's geometry, dictated by its density, appeared to be extremely close to flat, a state of delicate balance that seemed improbable without an underlying mechanism. A universe even slightly denser or less dense in its earliest moments would have quickly evolved into a dramatically curved cosmos, either collapsing upon itself or expanding too rapidly for structure to form. The observed near-perfect flatness demanded explanation. Finally, theoretical physics predicted an overabundance of magnetic monopoles and other exotic relics, which should have been created during the high-energy conditions of the early universe. Yet no such relics were detected. Classical Big Bang theory provided no natural mechanism for why these particles were absent. Inflation offered a revolutionary solution to all three of these problems. In this scenario, a tiny fraction of a second after the Big Bang, the universe underwent a brief period of exponential expansion. During this phase, the scale of space increased by many orders of magnitude, stretching and smoothing the fabric of the cosmos. Regions that were once microscopically close were blown apart to cosmic scales. Explaining the uniformity of the CMB and solving the horizon problem at the same time, inflation naturally drives the universe toward flatness. Any initial curvature becomes negligible as space stretches, just as wrinkles in a balloon's surface flatten when the balloon inflates. Similarly, the density of unwanted relic particles, like magnetic monopoles, is diluted to near zero. Explaining their absence today with one elegant mechanism. Inflation addressed puzzles that had challenged cosmologists for decades. The physics behind inflation involves a hypothetical energy field, often called the inflaton. This field dominated the universe during the inflationary epoch, providing a repulsive form of energy that drove exponential expansion. As inflation ended, the energy of the inflaton field decayed into ordinary particles, reheating the universe and giving rise to the hot, dense state described by the classical Big Bang theory. In this way, inflation is not an alternative to the Big Bang, but an extension, a prelude that explains how the universe reached the conditions we can observe. One of the most remarkable consequences of inflation is that it transforms quantum fluctuations into cosmic structure. Tiny random variations in the inflaton field were stretched to macroscopic scales, seeding the formation of galaxies, clusters, and superclusters. These primordial fluctuations, initially invisible, are now imprinted in the CMB, allowing cosmologists to reconstruct the early universe with extraordinary precision. Without inflation, the origin of these structures would remain mysterious. Inflation also revolutionized our perspective on the universe as a whole. Some models predict eternal inflation, in which inflationary regions continue to spawn bubble universes, each with its own physical properties. In this view, our observable universe is just one bubble in a vast, possibly infinite, multiverse. The constants of nature, the laws of physics, and even the dimensionality of space could vary from one bubble to another. If true, inflation implies that the universe is far more diverse, strange, and expansive than we could have imagined a century ago. Observational support for inflation has grown steadily. Satellite missions such as COBE, WMAP, and Planck have mapped the CMB with unprecedented precision, revealing subtle anisotropies and temperature fluctuations predicted by inflationary models. These measurements show the fingerprints of quantum fluctuations amplified to cosmic scales, providing compelling evidence that inflation occurred. While some details remain uncertain, such as the exact shape of the inflaton potential or the precise energy scale, the overall framework has proven remarkably successful. Inflation also reshapes our philosophical understanding of cosmic beginnings. It suggests that the universe is not merely expanding, but that the very fabric of space-time underwent dramatic stretching at its earliest moments. Concepts like before the Big Bang become subtle or even meaningless, as time itself may have emerged during the inflationary phase. The universe is not only vast, but also layered with processes that transcend ordinary intuition. Finally, inflation illustrates a profound connection between the quantum and the cosmic. Fluctuations that originate in the realm of subatomic particles, guided by the rules of quantum mechanics, are magnified to form galaxies, clusters, and the large-scale structure of the universe. The cosmos becomes a bridge between the infinitely small and the infinitely large, a testament to the unity of physical law across scales. Cosmic inflation, therefore, is not just a technical solution to theoretical puzzles. It is a conceptual revolution, reshaping our understanding of the universe's origins, the nature of spacetime, and the connection between quantum mechanics and cosmology. It opens the door to questions that extend beyond observation, inviting speculation about multiple universes, the emergence of time, and the ultimate structure of reality itself. Cosmic inflation is more than a concept. It is a dynamic process governed by the physics of energy fields and the structure of spacetime. At the heart of this process lies the inflaton field, a hypothetical energy field that dominated the universe during its earliest fraction of a second. The inflaton's potential energy acted like a repulsive force, counteracting gravity and driving the rapid exponential expansion that defines inflation. The mathematics of the inflaton field is intricate but elegant. In essence, the potential energy of the field remained nearly constant during inflation, providing a uniform push that caused space itself to stretch at incredible rates. This expansion was not linear or gradual. It was exponential, meaning that in an instant, distances between points in space grew by an enormous factor. A region smaller than a proton could be stretched to cosmic scales, smoothing out irregularities and creating a universe remarkably uniform on large scales. Different models of inflation propose variations in the shape and behavior of the inflaton potential. In slow-roll inflation, the field gradually rolls down a flat potential, maintaining nearly constant energy density and sustaining rapid expansion. In chaotic inflation, first suggested by Andre Lind, the inflaton field can start from random high-energy configurations, naturally leading to exponential expansion in some regions. Each model provides a slightly different prediction for the detailed structure of the universe, offering subtle clues that cosmologists can test through observations of the CMB and large-scale galaxy distributions. One of the most fascinating consequences of inflation is the amplification of quantum fluctuations. In the microscopic world, uncertainty and randomness are fundamental. Tiny variations in the inflaton field, normally insignificant on small scales, were stretched to macroscopic dimensions by the exponential expansion of space. These fluctuations became the initial density variations that later grew under gravity into the cosmic web of galaxies, clusters, and voids. Essentially, the universe's largest structures trace their origin to quantum jitters occurring when the cosmos was unimaginably small. These quantum seeds are printed in the cosmic microwave background. Observations by satellites like WMAP and Planck have detected temperature variations at the level of millionths of a degree, minute irregularities that correspond exactly to predictions from inflationary theory. Without these quantum fluctuations, the universe would have remained almost perfectly smooth, and galaxies, stars, planets, and life might never have formed. In this sense, inflation provides a direct link between the subatomic and the cosmic, demonstrating how the smallest scales influence the largest. Inflation also explains the horizon and flatness problems in a precise, testable way. By expanding space exponentially, inflation allowed regions that now appear widely separated to have once been in causal contact, equalizing temperatures and densities. Similarly, the rapid stretching drove the universe towards spatial flatness, making any initial curvature imperceptible on large scales. These solutions, initially theoretical, are strongly supported by the detailed uniformity and geometry observed in the CMB. Another intriguing aspect of inflation is the concept of eternal inflation. In some models, inflation never completely ends. While it stops in regions like ours, giving rise to the Big Bang and the observable universe, it continues elsewhere, spawning a multiverse of bubble universes. Each bubble could have different physical constants, laws of physics, or dimensions of space. This concept challenges our traditional view of the universe as a singular entity, suggesting instead a vast, possibly infinite, collection of universes, each with its own story, despite its successes. Cosmic inflation also leaves profound questions unanswered. What exactly is the nature of the inflated field? How did inflation begin, and what caused it to end in our region of space? Are there observable consequences of other bubbles in a multiverse, or will these remain forever beyond our reach? These mysteries sit at the frontier of modern physics, where quantum mechanics, general relativity, and cosmology intersect. From a practical standpoint, inflation transforms our understanding of the early universe. It provides a framework that unites classical cosmology, quantum physics, and observational astronomy. It explains why the universe is uniform, flat, and structured, while also giving rise to the galaxies and cosmic patterns we observe today. By combining theory and observation, inflation allows us to reconstruct a narrative that stretches from quantum jitters in the first tiny moments to the vast, star-filled cosmos surrounding us in essence. Inflation reveals a universe that is far stranger, larger, and more interconnected than we could have imagined. It is a cosmos where microscopic uncertainty shapes the grandeur of galactic filaments, where space itself is dynamic, and where multiple universes might exist beyond the limits of observation. It challenges our intuition and invites a deeper reflection on the nature of reality, observational. Advances continue to test and refine our understanding of inflation. By mapping the polarization of the CMB, measuring gravitational waves, and analyzing the distribution of galaxies across cosmic time, astronomers hope to uncover additional signatures of inflation. Each discovery deepens our understanding of the universe's earliest moments and the processes that gave rise to its remarkable complexity. Cosmic inflation, therefore, is not just a solution to technical problems in cosmology. It is a transformative lens through which we view the origin, structure, and potential multiplicity of the universe. By connecting the quantum and the cosmic, it provides insight into how randomness, energy, and expansion shaped a universe capable of harboring stars, planets, and life. The story of inflation is a story of the universe itself, an unfolding epic that began in a fraction of a second and continues to shape reality on the largest scales. The theory of cosmic inflation is elegant and compelling, but, like all scientific theories, it requires observational support. Fortunately, the universe itself provides a rich archive of evidence, allowing cosmologists to test predictions of inflation with remarkable precision. Among the most important clues is the cosmic microwave background CMB, the faint afterglow of the Big Bang. The CMB, discovered in 1965 by Arno Penzias and Robert Wilson, is a snapshot of the universe when it was roughly 380,000 years old. At that time, the universe cooled enough for photons to decouple from matter, allowing light to travel freely through space. This radiation, now stretched to microwave wavelengths by billions of years of cosmic expansion, carries imprints of the universe's earliest conditions. Inflation predicts that the CMB should exhibit minute temperature fluctuations, tiny differences in density and energy, originating from quantum fluctuations during inflation. Satellite missions, beginning with COBE and followed by WMAP and Planck, have mapped these fluctuations with increasing precision. These maps reveal a pattern of hot and cold spots across the sky, consistent with the statistical distribution expected from inflationary models. The fact that the observed fluctuations match theoretical predictions provides compelling evidence that inflation occurred another critical observational signature of inflation is the large-scale structure of the universe. Galaxies are not randomly scattered. They form clusters, filaments, and voids that trace a cosmic web. The statistical properties of this structure, the distribution of galaxy clusters, the size of voids, and the patterns of filamentary structures match the seeds predicted by inflationary quantum fluctuations. Essentially, the arrangement of galaxies across billions of light-years is a magnified echo of the earliest quantum. Jitters, gravitational waves provide an additional potential window into inflation. The rapid stretching of space-time during inflation should generate a faint background of primordial gravitational waves. Detecting these waves would offer direct evidence of the inflationary epoch and provide information about the energy scale at which inflation occurred. Experiments such as BICEP, Polar Bear, and future space missions aim to measure the subtle polarization patterns in the CMB that could reveal these gravitational waves. A confirmed detection would be a landmark achievement, connecting the physics of quantum fields to the grandest cosmic scales. Inflation also helps explain observed properties of the universe that might otherwise seem puzzling. The near-uniform temperature of the CMB, the flatness of space, and the absence of unwanted relic particles all find natural explanations within the inflationary framework. These features, previously seen as fine-tuned or improbable, emerge naturally from a brief period of exponential expansion. Observations continue to refine our understanding, placing tight constraints on the parameters of inflationary models, such as the shape of the inflaton potential and the duration of the inflationary epoch. The combination of theory and observation has made inflation one of the most predictive frameworks in cosmology. By comparing models to CMB anisotropies and the distribution of galaxies, cosmologists can narrow down the plausible scenarios for how inflation occurred. The success of these predictions demonstrates that inflation is more than a theoretical curiosity. It is a robust framework that explains features of the universe across scales, from subatomic fluctuations to the cosmic web. Yet, despite its successes, challenges remain. Different inflationary models predict subtle variations in the patterns of CMB anisotropies, gravitational waves, and galaxy formation. Observations so far are consistent with many of these models, but distinguishing between them requires ever more precise measurements. Moreover, confirming the existence of a multiverse, if eternal inflation is correct, remains beyond current observational capabilities. These challenges make the study of inflation a vibrant, ongoing frontier in cosmology. Ultimately, the evidence for inflation demonstrates a profound connection between the microscopic and the cosmic. Quantum fluctuations in a fraction of a second, magnified by rapid expansion, gave rise to the galaxies, clusters, and voids we observe today. Observations of the CMB and large-scale structure provide a window into these earliest moments, confirming the remarkable predictive power of inflationary theory. Inflation also emphasizes the interplay between observation and theory in modern science. Theoretical predictions guide observations, and observations refine and constrain theory. This iterative process has transformed our understanding of the early universe, revealing a cosmos far stranger and more intricate than previously imagined. It has also expanded the scope of human inquiry, suggesting that the universe may be one bubble among countless others, each with its own laws and structures. In the next section, we will explore the implications of inflation for the multiverse and the ultimate fate of the cosmos, completing Part 4 and looking at the vast possibilities that extend beyond our observable universe. The Big Bang is often described as the beginning of everything space, time, and matter itself. Yet this statement raises one of the most profound questions in cosmology. What, if anything, existed before the Big Bang? To probe this question, we must consider both the physics that governs the earliest universe and the philosophical implications of time itself. Classical Big Bang theory describes the universe's evolution from an initial hot, dense state onward. It does not, however, provide an account of what preceded that moment or whether such a question is even meaningful. According to general relativity, as we approach the singularity, the infinitely dense point at the origin of the Big Bang, the equations themselves break down. Space-time ceases to behave according to known physics, and our concepts of before and after may lose meaning. In this sense, asking what came before the Big Bang could be akin to asking what is north of the North Pole, a question that challenges the very framework of understanding. Despite these limitations, physicists have proposed several scenarios that extend beyond the classical singularity. One influential idea is the cyclic universe. In this model, the universe undergoes infinite cycles of expansion and contraction. Each Big Bang is followed by a period of expansion, eventual cooling, and then a contraction culminating in a big crunch, which triggers the next Big Bang. In this view, the Big Bang is not the ultimate beginning, but one phase in an eternal cosmic rhythm. Such models have been refined using string theory and brane cosmology, suggesting that our universe may exist on a higher dimensional membrane that collides periodically with other membranes, generating cycles of creation and destruction. Another proposal comes from quantum cosmology, which attempts to apply the principles of quantum mechanics to the universe as a whole. In this framework, the universe is described by a wave function, capturing all possible histories and configurations. Stephen Hawking and James Hartle developed the no-boundary proposal, suggesting that time itself becomes imaginary near the Big Bang, smoothing out the singularity. In this scenario, the universe has no true beginning. Instead, it emerges from a quantum regime where the classical distinction between past and future dissolves. Time, as we understand it, only emerges after the universe reaches a scale where classical physics applies. Other speculative ideas include the concept of a pre-Big Bang vacuum, a primordial state dominated by high-energy fields that existed before conventional spacetime emerged. In some string theory-inspired models, this vacuum contains fluctuations that eventually trigger the inflationary epoch, giving rise to a universe like ours. These ideas suggest that the Big Bang is not an absolute beginning, but a transition from one form of existence to another, a bridge from a pre-universe to the cosmos we observe today, cosmologists. Also consider the role of entropy and the arrow of time. In our observable universe, time has a direction. Entropy increases, galaxies evolve, stars age, and life emerges. But in a pre-Big Bang scenario, the concept of entropy might behave differently. Some models propose a time-symmetric universe where the arrow of time reverses across the Big Bang, or where multiple universes exist with opposing temporal directions. These ideas challenge intuition and force us to reconsider what we mean by before and after in a cosmic context. Observationally, testing these hypotheses is extremely difficult. The observable universe carries only limited information about its earliest stages. The cosmic microwave background reveals conditions after recombination, and gravitational waves may offer insights into inflation, but direct evidence of a pre-Big Bang state remains elusive. Nevertheless, theorists use mathematical consistency, the laws of quantum mechanics and general relativity to explore the possibilities, seeking models that make testable predictions within the constraints of observation. The question of what came before the Big Bang also intersects with philosophical and metaphysical considerations. If time itself began with the Big Bang's causality, the principle that every effect has a cause may not apply in the traditional sense. In this view, the universe could exist as a self-contained entity, with no need for a prior cause or temporal origin. This challenges our instinctive notions of beginnings and endings, suggesting that the cosmos may be fundamentally different from the human-scale experiences of time and space. Ultimately, The exploration of pre-Big Bang scenarios highlights the limits of human knowledge and the ingenuity of theoretical physics. By stretching the imagination and combining quantum mechanics, general relativity, and cosmology, scientists attempt to peer into the realm beyond the observable universe. While definitive answers may remain beyond reach, these investigations reveal a universe far more complex, mysterious, and profound than the simple narrative of a single beginning. In the next section, we will explore specific pre-Big Bang models, including cyclic universes, quantum bound scenarios, and multiverse implications, diving deeper into how the cosmos might extend beyond the origin we traditionally associate with the Big Bang. When contemplating what existed before the Big Bang, cosmologists have proposed several theoretical frameworks, each attempting to extend our understanding of the universe beyond the limits of classical physics. Among the most influential is the cyclic universe model. In this scenario, the universe is not a singular event, but a recurring cycle of birth, expansion, contraction, and rebirth. Each Big Bang is followed by billions of years of expansion, a gradual cooling, and eventual contraction culminating in a big crunch, which sets the stage for the next Big Bang. Modern cyclic models are often inspired by brane cosmology, a branch of string theory. In this framework, our universe exists on a three-dimensional membrane, or brane, embedded within a higher dimensional space. Occasionally, this brane may collide with another brane, releasing tremendous energy and initiating a new Big Bang. These collisions could be periodic, giving rise to an eternal cosmic rhythm. In such a model, the universe is timeless in a sense. There is no absolute beginning or end, only an infinite succession of cosmic epochs. Another prominent idea is the concept of a quantum bounce. Loop quantum cosmology, an approach derived from quantum gravity, suggests that the universe never reaches a true singularity. Instead, the immense density of the early universe triggers quantum gravitational effects, causing a collapse to rebound into expansion. In this model, the universe we observe today emerged from the contraction of a previous universe. This bounce replaces the classical singularity with a finite, calculable state governed by quantum rules, providing a mathematically consistent way to extend the history of the cosmos backward in time. Some models also posit a pre-Big Bang vacuum filled with fluctuating high-energy fields. In this view, the Big Bang is not the ultimate origin, but a transition from a primordial quantum state to the expanding universe we observe. Tiny fluctuations in this vacuum could have triggered the inflationary epoch, seeding the density variations that eventually led to galaxies, stars, and planets. These ideas connect the beginning of our observable universe to processes that predate time itself, offering a glimpse into a realm fundamentally different from the classical cosmos. The multiverse hypothesis provides yet another perspective. If inflation is eternal, then countless bubble universes may exist beyond our observable horizon, each arising from a local inflationary event. Our universe could be just one bubble among an infinite sea of universes, each with its own physical laws and constants. In this framework, what we call the Big Bang is merely a local occurrence, the birth of our bubble, while the broader multiverse continues indefinitely. Observers in other universes might experience entirely different histories, dimensions, or even directions of time. These pre-Big Bang models, while speculative, are constrained by mathematics and physical law. They are not flights of fantasy, but logical extensions of known principles, such as general relativity and quantum mechanics. By exploring scenarios like the cyclic universe, quantum bounce, or multiverse, physicists aim to answer questions about the origin, structure, and ultimate nature of reality. Each model provides unique insights, suggesting that the universe may be far larger, older, and stranger than what we can directly observe. Testing these models remains a formidable challenge. Observational evidence is limited to the cosmic structures, background radiation, and gravitational waves accessible from within our bubble universe. Yet scientists hope that subtle signatures in the polarization of the cosmic microwave background, in primordial gravitational waves, or in large-scale cosmic structures may offer indirect clues about what happened before the Big Bang. Even tiny hints could revolutionize our understanding, revealing the broader context in which our universe emerged. Ultimately, pre-Big Bang models invite us to rethink the concept of a beginning. The classical view of a singular origin, where time and space emerged abruptly, may be replaced by a more nuanced understanding, in which the universe is part of a vast, ongoing, and possibly infinite process. These theories challenge intuition, extend the boundaries of physics, and underscore the humility required when confronting questions about the ultimate nature of reality. In the next section, we will explore the philosophical and scientific implications of these pre-Big Bang ideas, including the nature of time, causality, and the possibility of multiple universes, bringing Part 5 to a reflective and comprehensive conclusion. Exploring what existed before the Big Bang challenges not only physics, but our most fundamental notions of reality. If the universe did not begin in a singular event, but is part of a cyclic process, a quantum bounce, or an eternal multiverse, then time itself may not be linear in the way we experience it. Concepts such as before and after, so central to human understanding, might only apply locally within our bubble universe. In this sense, the Big Bang is not an absolute beginning, but a transitional moment, a bridge between different states of reality. The philosophical implications are profound. The classical question, "Why does the universe exist?" becomes more nuanced. If the universe is eternal in some form through cycles or quantum processes, the notion of a singular origin is replaced by a framework in which existence itself is self-sustaining. In a multiverse scenario, our universe is merely one of countless possibilities, each realized in different regions of space-time. This perspective challenges traditional ideas of causality, suggesting that the cosmos may be governed by principles beyond simple cause and effect relationships as we know them. Pre-Big Bang models also invite reflection on the limits of scientific knowledge. The earliest moments of the cosmos lie at the intersection of general relativity and quantum mechanics, a domain where our current theories are incomplete. Singularities, quantum fluctuations, and high-energy fields create conditions that push our mathematics and intuition to their limits. Observations of the cosmic microwave background and gravitational waves offer glimpses, but the true nature of pre-Big Bang reality may remain forever beyond direct detection. Yet even speculative models are valuable, providing a framework to guide research, inspire experiments, and sharpen our understanding of the cosmos. The cyclic universe has striking implications for cosmology and philosophy. If the cosmos undergoes infinite cycles, then every Big Bang may have predecessors and successors. Life, matter, and structure emerge, evolve, and eventually dissolve, only to reappear in future cycles. In this framework, the universe is not finite in time, but part of an ongoing cosmic rhythm. Humanity's brief moment in the vast timeline of the cosmos becomes a single note in an eternal symphony. Quantum bounce models similarly reshape our understanding of origin. They suggest that extreme conditions at the end of one universe can naturally give rise to the next. Here, the universe is resilient, capable of renewal, and free from the need for an initial singularity. The laws of physics, rather than being arbitrary, are encoded in a dynamic process that links past, present, and future in a seamless continuum. The multiverse concept extends these ideas even further. If inflation is eternal, bubble universes may continually emerge, each with its own physical laws. Our universe, with its familiar constants and structures, could be one of countless variations shaped by local fluctuations in the inflattened field. In such a cosmos, questions about fine-tuning, why the universe seems perfectly suited for life may be answered statistically. We exist in a universe capable of supporting life because only such universes can host observers. This perspective transforms philosophical debates into probabilistic reasoning within a vast cosmic landscape. These models also inspire new questions about the nature of time and causality. In some cyclic and quantum scenarios, time may be symmetric, flowing differently in different regions, or emerging only after a transition like the Big Bang. Causality, traditionally viewed as linear, may be more flexible at the level of the cosmos. Our intuition, shaped by experiences on Earth, may not apply at the extremes of cosmic scale and quantum gravity. Accepting this challenges our sense of certainty and encourages humility in confronting the universe's deepest mysteries. Finally, pre-Big Bang ideas illuminate the profound connection between theory, observation, and imagination. While direct evidence may be scarce, the interplay of mathematics, physics, and cosmology allows scientists to explore scenarios beyond human experience. By considering cycles, bounces, and multiple universes, we expand the scope of inquiry from our observable cosmos to the vast possibilities that lie beyond. These concepts transform our understanding of beginnings, endings, and the nature of existence itself. In conclusion, contemplating what came before the Big Bang is not merely an academic exercise. It reshapes our understanding of time, causality, and the cosmos, offering glimpses into a universe that may be eternal, self-renewing, and unimaginably vast. Whether through cyclic rhythms, quantum bounces, or an endless multiverse, the cosmos challenges us to think beyond intuition, to embrace mystery, and to recognize that the origin of reality may be far more complex and more beautiful than any singular event could convey. While the Big Bang and cosmic inflation dominate modern cosmology, the quest to understand the universe has inspired alternative theories that challenge or extend the standard model. These competing ideas arise from both observational puzzles and theoretical curiosity, each offering unique insights into the origins, evolution, and fate of the cosmos. One of the earliest challenges came from the steady-state theory, proposed in the mid-20th century by Fred Hoyle, Thomas Gold, and Hermann Bondi. According to this model, the universe has no beginning or end in time and maintains a constant average density. As galaxies move apart due to cosmic expansion, new matter is continuously created to fill the gaps, ensuring an unchanging large-scale appearance. In this framework, the universe is eternal and homogeneous, and the concept of a singular Big Bang is unnecessary. The steady-state theory elegantly addressed philosophical discomfort with a cosmic beginning, suggesting a universe with no preferred origin. However, it struggled to account for key observational evidence. The discovery of the cosmic microwave background CMB in 1965 provided a snapshot of an early hot universe, directly supporting a Big Bang origin. Moreover, the abundance of light elements like helium and deuterium, consistent with predictions from Big Bang nucleosynthesis, posed additional challenges to the steady-state model. While largely abandoned today, it remains historically important, illustrating how cosmology evolves through hypothesis, observation, and falsification. Another compelling alternative comes from cyclic and ekpyrotic models, which we touched on in the discussion of pre-Big Bang scenarios. These models suggest the universe undergoes periodic expansions and contractions, eliminating the need for a singular beginning. In the ekpyrotic scenario, inspired by string theory, two three-dimensional branes collide in higher dimensional space, producing a Big Bang-like event. Unlike classical inflation, which starts from a quantum field in a vacuum, these models envision a dynamic cosmic landscape where collisions, contractions, and expansions drive the universe's evolution. The quantum gravity approach offers further alternatives. In classical general relativity, the Big Bang singularity is inevitable, but quantum corrections may prevent infinite densities. Loop quantum cosmology, for example, replaces the singularity with a quantum bounce, suggesting the universe is cyclic at the deepest level. In this framework, the laws of physics themselves evolve across cosmic epochs, connecting past and future universes in a continuous chain. These models are mathematically sophisticated, providing a consistent way to extend cosmology beyond the limitations of classical theory. Modified gravity theories also provide competing perspectives. Instead of assuming dark energy or dark matter, some models propose alterations to Einstein's general relativity on cosmic scales, by changing the behavior of gravity at extreme distances or energies. These theories aim to explain the observed expansion of the universe and its large-scale structure without invoking unknown forms of matter or energy. While still speculative, these ideas illustrate the diversity of approaches in modern cosmology and the willingness of scientists to question fundamental assumptions. Observational challenges continue to motivate alternative models. For example, discrepancies in the measurement of the Hubble constant, the rate at which the universe is expanding, suggest that our understanding of cosmic expansion may be incomplete. Different methods, such as observing supernova versus the cosmic microwave background, produce slightly different values. Some theorists propose that these tensions could point to new physics beyond the standard model, potentially involving alternative cosmologies or modifications to general relativity. Another intriguing direction involves emergent and holographic universe models. These propose that space-time and gravity may not be fundamental but emergent phenomena, arising from underlying quantum information. In this view, the universe could appear to have a big bang from our perspective, while fundamentally arising from deeper, timeless structures. This approach is still highly theoretical, but offers a radically new way to think about cosmology, connecting quantum mechanics, gravity, and information theory. Despite these competing theories, the Big Bang and inflationary model remain the most successful in explaining observations. Yet alternative models play a crucial role in advancing science. By challenging assumptions and exploring new possibilities, they push cosmologists to refine measurements, improve models, and confront uncertainties. The universe, as revealed by these debates, is both richer and stranger than any single theory can capture. Competing theories also highlight the profound interplay between observation, mathematics, and philosophy in cosmology. Every alternative model is a lens through which we question the nature of time, space, and existence itself. Some models may eventually be ruled out, while others may lead to revolutionary insights. In the pursuit of understanding, it is this willingness to explore the unknown that drives human curiosity and expands the boundaries of knowledge. In the next section, we will delve into challenges posed by dark matter, dark energy, and cosmic anomalies, examining how these mysteries inspire new theoretical frameworks and ongoing debates among cosmologists. Even with the success of the Big Bang and inflationary models, certain cosmic phenomena continue to challenge our understanding. Chief among these are dark matter and dark energy, mysterious components that appear to dominate the universe's mass and energy content, yet remain largely invisible. Together, they account for roughly 95% of the universe, leaving only 5% composed of ordinary matter, the stars, planets, and gas we observe directly. Dark matter was first inferred in the 1930s by Fritz Zwicky, who noticed that galaxies and clusters moved faster than expected based on visible mass alone. Further evidence came from the rotation curves of galaxies. Stars at the outer edges of galaxies orbit much faster than predicted, implying the presence of unseen mass. This missing mass cannot be accounted for by ordinary matter, and its nature remains one of the most pressing questions in cosmology. To explain dark matter, scientists have proposed a variety of candidates. Weakly interacting massive particles, WIMPs, exions, and sterile neutrinos are among the leading possibilities. Despite decades of experimental searches, no definitive detection has been made. This has led some theorists to propose alternative gravity models, such as modified Newtonian dynamics, MOND, or extensions to general relativity, which attempt to reproduce the observed galactic motions without invoking unseen matter. These competing theories challenge the conventional cosmological framework and highlight the tension between observation and theoretical expectation. Dark energy. Discovered in the late 1990s through observations of distant supernova, presents an equally profound puzzle. The expansion of the universe is accelerating, contrary to the expectation that gravity should gradually slow it down. Dark energy is the term given to the unknown cause of this acceleration, representing roughly 70% of the universe's energy content. Its origin, whether as a cosmological constant, a dynamic field, or a manifestation of modified gravity, remains uncertain. The existence of dark energy and dark matter has inspired alternative cosmological models that extend or modify the Big Bang paradigm. For instance, some cyclic or ekpyrotic models incorporate dark energy as a driver of contraction and expansion phases, linking these mysterious components to the broader evolution of the cosmos. Others suggest that anomalies in galaxy formation or cosmic expansion may point to physics beyond the standard model, potentially reshaping our understanding of space-time itself. Beyond dark matter and dark energy, cosmologists have identified cosmic anomalies that challenge the conventional view. For example, large-scale structures like the cosmic cold spot or unexpected alignments in the cosmic microwave background. CMB hint at features not fully explained by standard inflationary models. These anomalies may reflect statistical fluctuations, observational limitations, or hints of new physics, including pre-Big Bang effects or multiverse interactions. The combination of dark matter, dark energy, and cosmic anomalies underscores a central theme in competing theories. The universe may be far more complex than our simplest models suggest. While the Big Bang and inflation explain many observations with remarkable accuracy, these unresolved mysteries motivate alternative frameworks that explore new possibilities. From modified gravity to extra dimensions, quantum effects, or multiverse connections, scientific exploration thrives on such challenges. Each anomaly, discrepancy, or unexplained phenomenon is not a failure, but an opportunity, a window into deeper layers of reality. By confronting these puzzles, cosmologists refine their models, test the limits of current physics, and develop innovative theories that may ultimately unify our understanding of the cosmos. In the next section, we will examine radical cosmological theories and cutting-edge ideas, including holographic universes, emergent spacetime, and other speculative frameworks that challenge conventional views, completing Part 6's exploration of competing perspectives. Beyond modifications to gravity or alternative explanations for dark matter and dark energy, cosmologists have begun exploring more radical frameworks that challenge our foundational understanding of space, time, and reality itself. These theories, while highly speculative, push the boundaries of modern physics and open new possibilities for how the universe may operate. One such idea is the holographic principle. Inspired by black hole thermodynamics and string theory, the holographic principle suggests that the information contained within a volume of space can be described entirely by data on its boundary. In other words, the universe might function like a hologram, with three-dimensional reality emerging from two-dimensional information encoded on the cosmos's edges. If correct, this framework radically redefines the nature of spacetime, implying that the universe we perceive is a projection from deeper, lower-dimensional laws. Closely related is the concept of emergent spacetime, which proposes that space and time are not fundamental entities, but arise from underlying quantum interactions. In this view, gravity itself could be an emergent phenomenon, the result of microscopic degrees of freedom obeying statistical laws. If space-time is emergent, then questions about the Big Bang or pre-Big Bang conditions may need to be reframed. What we consider the origin of the universe could instead be a phase transition in a more fundamental substrate. Other speculative frameworks explore the possibility of variable physical constants or multiple dimensions beyond our perception. In string theory, for instance, extraspatial dimensions exist but are compactified or hidden from direct observation. These dimensions can influence cosmic evolution, particle interactions, and even the apparent values of fundamental constants. In a multiverse context, different regions of the cosmos could exhibit different constants, leading to entirely distinct universes, each with its own physical laws. Quantum mechanics also inspires radical perspectives, such as the many worlds interpretation, which proposes that every quantum event creates branching realities. Applied cosmologically, this could imply that all possible histories of the universe exist simultaneously, each realized in a separate branch or universe. In such a framework, the Big Bang may represent a local event within a vastly larger quantum landscape. Additionally, loop quantum gravity suggests that space-time itself has a discrete, granular structure at the smallest scales. These quanta of space prevent singularities and allow for scenarios like the quantum bounce, connecting previous and current universes in a continuous, non-singular history. Such models are consistent with a universe that evolves in cycles, linking radical quantum effects to observable cosmic structures. Despite their speculative nature, these radical theories serve a critical role in scientific progress. They challenge deeply ingrained assumptions, encourage new experiments, and often lead to testable predictions. For example, emergent spacetime models suggest subtle correlations in the cosmic microwave background, while holographic models can constrain the entropy and information content of the universe. Even if some theories are ultimately disproven, their exploration expands the conceptual landscape, inspiring innovation in both theory and observation. Radical cosmologies also highlight a central theme in competing theories. The universe may be far stranger than our human intuition allows. Space, time, and matter, the familiar fabric of reality, may be emergent, holographic, or fundamentally quantum. Observations of galaxies, cosmic expansion, and radiation provide only a partial glimpse, leaving the deepest structures of reality to theoretical investigation. These frontiers remind us that science is as much about imagination and conceptual daring as it is about measurement and calculation. In the final section of Part 6, we will summarize how competing and radical theories collectively enrich cosmology, highlighting the ongoing dialogue between observation, theory, and speculation that drives our understanding of the universe. Despite the many competing theories and radical speculations, modern cosmology has converged on a well-supported framework for understanding the universe's origins. The Big Bang Theory complemented by cosmic inflation. These models provide a coherent explanation for a wide range of observations, from the expansion of galaxies to the properties of the cosmic microwave background (CMB) and the abundance of light elements. The Big Bang Theory posits that the universe began approximately 13.8 billion years ago from a hot, dense state. This initial state was not an explosion in space, but rather an expansion of space itself, creating the framework within which matter, energy, and time evolved. Observational evidence for this model is overwhelming. Edwin Hubble's discovery in the 1920s that galaxies are receding from one another provided the first clear sign that the universe is expanding, implying that it was smaller, hotter, and denser in the past. The cosmic microwave background (CMB), discovered in 1965 by Arno Penzias and Robert Wilson, offers further confirmation. This faint, uniform radiation is a relic of the early universe, emitted approximately 380,000 years after the Big Bang, when atoms first formed and the universe became transparent to light. The CMB's precise temperature fluctuations reveal the seeds of cosmic structure, the slight density variations that would eventually grow into galaxies and clusters. Its discovery provided one of the most compelling pieces of evidence for the Big Bang, directly linking theory to observable data. Big Bang nucleosynthesis is another critical pillar of the scientific consensus. In the first few minutes after the universe began, protons and neutrons combined to form light nuclei, including hydrogen, helium, and trace amounts of lithium. Observations of primordial abundances across the cosmos closely match theoretical predictions, providing a powerful confirmation of the model. The consistency between predicted and observed elemental ratios strengthens the case that the Big Bang accurately describes the universe's early history. Cosmic inflation, proposed in the 1980s by Alan Guth and others, refines this picture. Inflation describes an extremely rapid expansion in the first fraction of a second after the Big Bang, solving several puzzles in cosmology. It explains the observed uniformity of the CMB across vast distances, despite regions being causally disconnected. This is known as the horizon problem. Inflation also accounts for the flatness problem, the observation that the universe's geometry is remarkably close to flat on large scales. By stretching space exponentially, inflation naturally produces a nearly uniform and flat universe while generating the small fluctuations that seed galaxies. While the Big Bang and inflationary models form the backbone of modern cosmology, science continues to grapple with unanswered questions. The precise nature of inflation, the origin of the inflated field, and the underlying physics at energy scales far beyond current experiments remain subjects of active research. Observations of gravitational waves, primordial density fluctuations, and other cosmic signatures may one day reveal more about these earliest moments. Scientific inquiry also recognizes the limitations of the classical Big Bang framework. Questions about what preceded the Big Bang, the fundamental nature of time and space, and the possible existence of a multiverse are approached cautiously. The prevailing scientific stance is not to speculate without evidence, but to construct models that can be tested, refined, or falsified through observation. This methodological rigor is a hallmark of the scientific process, ensuring that cosmological theories remain grounded in empirical reality rather than unfettered imagination. In conclusion, while the cosmos is full of mystery and competing ideas, the scientific consensus rests on the Big Bang, cosmic inflation, and supporting evidence from the CMB, nucleosynthesis, and large-scale structure. These models offer a robust framework for understanding the universe's origins, providing testable predictions and a coherent narrative that aligns with observation. In the next section, we will examine how scientists interpret data from the early universe, the role of observation and experiment, and the interplay between theory and evidence. Science relies on observation, measurement, and theoretical interpretation to uncover the universe's origins. In cosmology, the challenge is magnified. The earliest moments of the cosmos are inaccessible to direct experiment, and much of the universe lies beyond our observable horizon. Yet through meticulous observation and advanced instrumentation, scientists have pieced together an extraordinary picture of cosmic history. The cosmic microwave background CMB serves as the most powerful observational tool for probing the early universe. By mapping tiny temperature fluctuations in the CMB, missions such as COBE, WMAP, and Planck have provided precise measurements of the universe's composition, geometry, and age. These fluctuations, on the scale of 1 part in 100,000, represent the seeds of galaxies and large-scale structures. Their patterns confirm predictions of inflationary theory, revealing a cosmos that is both uniform and structured in remarkably consistent ways. Redshift surveys of galaxies offer another window into cosmic evolution. By measuring how light stretches as galaxies move away from us, astronomers determine the rate of expansion and reconstruct the universe's history. Observations of distant type Ia supernova revealed the accelerating expansion, leading to the discovery of dark energy. Such data illustrate how careful measurement can uncover phenomena that are invisible yet dominate the cosmos. Elemental abundances are another line of evidence. Observations of hydrogen, helium, and lithium in ancient stars and interstellar gas match the predictions of Big Bang nucleosynthesis. This alignment between theory and observation reinforces confidence in the standard cosmological model and provides a quantitative understanding of the universe's earliest minutes. Gravitational waves, first directly detected in 2015, offer a new frontier in cosmological observation. Ripples in spacetime generated by massive astrophysical events, and potentially by inflationary processes in the early universe, carry information inaccessible by traditional electromagnetic observations. Future detection of primordial gravitational waves could confirm inflationary models and even provide indirect insight into pre-Big Bang conditions. Science's strength lies in the interplay between theory and observation. Theoretical models, like the Big Bang and inflation, generate predictions that guide observation. Conversely, data from telescopes, satellites, and detectors refine, constrain, or even challenge theories. For example, discrepancies in the measurement of the Hubble constant, the universe's expansion rate, have prompted new discussions about dark energy, potential modifications to general relativity, and alternative cosmological models. These ongoing debates exemplify how observation drives theory and vice versa. Moreover, cosmologists recognize the importance of consistency across multiple lines of evidence. Observations of the CMB, galaxy clustering, supernova, and elemental abundances all converge to support the Big Bang framework. Where anomalies appear, such as the cosmic cold spot or tensions in Hubble constant measurements, scientists explore new theories, alternative models, or potential observational errors. This rigorous approach ensures that cosmology remains a testable science, grounded in empirical reality. Importantly, scientific interpretation does not shy away from uncertainty. Cosmologists embrace the provisional nature of models, understanding that each new observation may refine or challenge prevailing theories. This humility differentiates science from speculation. Conclusions are drawn based on evidence, and theoretical extensions remain contingent on observational support. Finally, the synthesis of evidence highlights the elegance and scope of modern cosmology. By combining insights from the smallest scales of quantum mechanics to the largest scales of cosmic structure, scientists construct a coherent narrative of the universe's past, present, and potential future. While questions remain about pre-Big Bang conditions, dark energy, or the ultimate fate of the cosmos, the robust framework built from observation and theory provides the most reliable understanding, currently achievable. In the next section, we will explore how science addresses the limits of knowledge, the role of speculation versus evidence, and what we can reasonably conclude about cosmic origins, completing Part 7. While modern cosmology provides a coherent narrative of the universe's history, science also recognizes its boundaries. The earliest instance of the cosmos fractions of a second after the Big Bang remain inaccessible to direct observation. Quantum effects at extreme energy scales, the behavior of spacetime at singularities, and potential pre-Big Bang conditions are areas where theoretical models outpace empirical verification. This does not diminish the value of these models, but underscores the cautious distinction between evidence-based conclusions and informed speculation. The Big Bang and inflation are supported by multiple lines of evidence. The expansion of the universe, the cosmic microwave background, elemental abundances, and the distribution of galaxies. However, questions about what preceded the Big Bang, the true nature of dark matter and dark energy, and the potential existence of a multiverse remain open. Scientists approach these topics carefully, using theoretical frameworks to generate predictions while acknowledging that some answers may be fundamentally inaccessible with current technology. The role of speculation in science is subtle but important. Speculative models such as cyclic universes, quantum bounces, and holographic cosmologies serve as laboratories for ideas, challenging conventional assumptions and suggesting new avenues for observation. While these models may never be directly confirmed, they influence the design of experiments, the interpretation of anomalies, and the development of new theoretical tools. In this sense, speculation is a creative partner to observation, guiding the scientific process while remaining anchored in rigor. One practical consequence of these limits is humility. We can construct robust models of cosmic evolution without claiming ultimate knowledge of the universe's origin. Science provides a framework for understanding the universe as it behaves and as it appears, not necessarily as an absolute truth about its ultimate cause. The distinction between what we can test and what we can imagine is central to scientific reasoning, ensuring that cosmology remains both ambitious and credible. Current scientific consensus allows us to reasonably conclude several key points. The universe is expanding. It originated from a hot, dense state approximately 13.8 billion years ago. Inflation likely shaped its large-scale uniformity, and the early universe produced the primordial elements we observe today. These conclusions are grounded in direct observation and robust theoretical modeling, forming the backbone of modern cosmology. Moreover, science equips us to explore the unknown with confidence, even in areas beyond direct measurement. Gravitational waves, high-precision cosmological surveys, and particle physics experiments continue to probe conditions near the universe's beginning. Each new observation has the potential to confirm, refine, or challenge prevailing theories, extending the frontier of knowledge while respecting the boundaries of evidence. Ultimately, the scientific approach to cosmic origins emphasizes curiosity, rigor, and openness. It balances bold theoretical ideas with meticulous observation, ensuring that claims remain testable and grounded. While ultimate answers about why the universe exists may remain elusive, we can understand the processes that shaped the cosmos, trace the evolution of matter and energy, and explore the profound implications of spacetime, quantum fields, and cosmic inflation. In conclusion, what science actually says about the universe is both profound and measured. It offers a coherent, evidence-based story of the universe's beginnings and evolution, while leaving room for mystery, exploration, and continued discovery. By combining observation, theory, and careful speculation, cosmology illuminates the origins of reality itself, guiding humanity's quest to understand its place in the cosmos. The question of whether another Big Bang could occur touches on some of the deepest mysteries in cosmology. To explore this, scientists examine the universe's long-term evolution, the role of dark energy, and theoretical models that extend beyond the classical Big Bang. Understanding these possibilities requires grappling with concepts of cosmic expansion, entropy, and the interplay of fundamental forces over billions or even trillions of years. Current observations indicate that the universe is expanding at an accelerating rate, driven by the mysterious force of dark energy. If this acceleration continues indefinitely, the cosmos may experience a big freeze or heat death in which galaxies drift apart. Stars burn out, and energy becomes increasingly diffuse. In such a scenario, the conditions for a second Big Bang appear highly unlikely, as matter and energy would be too dispersed to collapse into a new singularity. However, alternative models suggest more cyclic or dynamic outcomes. Cyclic cosmologies propose that the universe undergoes phases of expansion and contraction. In these models, the universe may eventually reach a point of maximum expansion, then contract under gravitational forces, potentially leading to a big crunch. If the contraction reaches sufficient density, it could trigger conditions analogous to a new Big Bang, restarting cosmic evolution. This vision of a cyclic universe offers a striking contrast to the one-way trajectory suggested by perpetual expansion. Quantum cosmology introduces additional possibilities. Some theories, including loop quantum gravity, suggest that singularities are replaced by quantum bounces, instead of an absolute beginning or end. The universe may pass through successive phases of compression and expansion, each Big Bang-like event emerging naturally from quantum gravitational effects. In this framework, a new Big Bang is not only possible but may be an inevitable feature of cosmic evolution. The concept of a multiverse also expands the notion of recurrence. In certain inflationary models, the universe continually spawns bubble universes through eternal inflation. Each bubble may experience its own Big Bang-like event independent of the fate of our observable cosmos. From this perspective, while another Big Bang might not occur within our universe, new universes with Big Bang conditions could constantly form in a larger, multiversal landscape. Entropy plays a central role in these scenarios. The second law of thermodynamics dictates that the universe's total entropy increases over time, presenting challenges for cyclic or recurring models. Some theorists propose mechanisms to reset or recycle entropy during contraction phases, allowing for repeated Big Bang-like events. Others suggest that quantum effects or exotic forms of matter could circumvent entropy constraints, maintaining the potential for renewal on cosmological timescales. Observational data provides limited guidance on these possibilities, while the current accelerating expansion favors a one-way trajectory. Uncertainties in the nature of dark energy leave room for alternative outcomes. Future measurements of cosmic acceleration, large-scale structure, and the behavior of dark energy could clarify whether contraction and recurrence are physically plausible. Ultimately, the question of another Big Bang highlights the interplay between theory, observation, and speculation in cosmology. While the standard model does not predict recurrence within our universe, cutting-edge theories suggest that cyclic processes, quantum effects, or multiverse dynamics could produce new Big Bang events under certain conditions. This remains one of the most profound and tantalizing questions in modern cosmology, bridging physics, philosophy, and human curiosity. In the next section, we will examine specific theoretical models that propose new Big Bangs, their underlying physics, and the evidence that might support or challenge them. Continuing our exploration of the universe's ultimate fate. Several advanced cosmological models propose scenarios in which a new Big Bang could occur. Though each relies on assumptions about physics far beyond current experimental verification, these models explore how the universe might cycle, bounce, or spawn entirely new regions of spacetime, offering fascinating insights into the potential recurrence of cosmic beginnings. One prominent class is the cyclic or ekpyrotic models. In these theories, the universe undergoes repeated phases of expansion and contraction. During a contraction phase, matter and energy collapse toward high densities, potentially creating conditions similar to those at the initial Big Bang. The ekpyrotic model, rooted in string theory, posits that our universe's Big Bang resulted from a collision between higher-dimensional branes in a multidimensional space. Such collisions could recur, generating successive universes or cosmic epochs. These models elegantly address certain cosmological puzzles, including the horizon and flatness problems, while offering a natural mechanism for recurring Big Bang events. Loop quantum cosmology offers another fascinating scenario. Traditional Big Bang models predict a singularity, a point of infinite density and temperature at the universe's origin. Loop quantum cosmology, however, replaces the singularity with a quantum bounce. Here, The laws of quantum gravity prevent infinite density from forming, instead causing a highly compressed universe to rebound and expand again. In this framework, Big Bang is not a unique beginning, but a phase in a potentially infinite series of expansions and contractions. Quantum bounces suggest that time and space themselves are cyclical at a fundamental level, allowing for recurring Big Bang-like events governed by quantum rules. Eternal inflation provides yet another perspective. In this model, inflation is not a singular event, but an ongoing process in a multiverse. Different regions of spacetime stop inflating at different times, creating pocket universes with Big Bang-like conditions. Each pocket can have its own physical constants, laws, and cosmic history. From this viewpoint, while our observable universe may continue expanding toward a heat death, countless other universes could be continuously formed through Big Bang-like events elsewhere in the multiverse. Observationally, direct evidence is difficult to obtain, but subtle signatures such as patterns in the cosmic microwave background or gravitational waves could provide indirect hints. Another speculative approach involves dark energy dynamics. If dark energy evolves over time rather than remaining constant, it could eventually reverse the universe's expansion. In such a scenario, the cosmos might collapse, concentrating energy and matter to trigger conditions conducive to a new Big Bang. This concept links the mysterious properties of dark energy directly to cosmic renewal, suggesting that the fate of the universe and the possibility of recurrence are intimately connected. While these models are mathematically sophisticated, they remain highly theoretical. Testing them requires observations at scales and energies far beyond current capabilities. For instance, detecting gravitational wave signatures from previous cycles or subtle imprints from bubble universes could provide indirect evidence. Particle physics experiments, high-precision cosmological surveys, and next-generation telescopes may eventually offer data to support or challenge these radical ideas despite uncertainties. These models illustrate a profound point. The universe may be far more dynamic and interconnected than our everyday experience suggests. The classical view of a singular beginning followed by endless expansion is not the only possible narrative. Through cyclic universes, quantum bounces, and multiverse processes, cosmology entertains the possibility of repeated cosmic births, each echoing the fundamental processes that shaped our universe. In the final section of Part 8, we will explore the philosophical and scientific implications of a recurring Big Bang, considering what such scenarios mean for the nature of time, existence, and humanity's place in an ever-evolving cosmos. Asterisk. The possibility of another Big Bang raises profound questions that bridge science, philosophy, and the human imagination. If the universe is capable of cycling through expansions and contractions, or if new universes emerge continuously through eternal inflation, our understanding of time, causality, and cosmic beginnings must be reconsidered. A recurring universe challenges the notion of a single origin. In classical cosmology, the Big Bang represents a unique, unrepeatable beginning, the moment when space, time, and matter came into existence. Cyclic or multiverse models suggest instead that beginnings may be local phenomena, with countless births occurring across spacetime. Each universe, or cosmic cycle, could have different physical laws, histories, and structures, hinting at a reality far more diverse and dynamic than our observable cosmos alone reveals. Philosophically, the idea of recurrence reshapes human perspective. In a cyclic universe, concepts like creation and end become relative. Time is no longer a linear, one-way flow, but a repeating or branching process. Existence may not have a singular starting point. Instead, life, matter, and energy participate in an ongoing cosmic rhythm. Such a vision encourages a sense of continuity, resilience, and connection across cosmic scales. Even as individual stars, galaxies and universes emerge and fade. Scientifically, contemplating recurrence inspires new approaches to observation and theory. Cosmologists search for subtle signatures of previous cosmic cycles, such as anomalies in the cosmic microwave background, patterns in gravitational waves, or correlations in large-scale structure. Each potential clue represents a window into phenomena far beyond our immediate reach, demonstrating the power of imagination guided by rigorous measurement. Recurring Big Bang models also intersect with fundamental physics, suggesting that quantum mechanics, gravity, and cosmology are deeply intertwined. Quantum bounces, brain collisions, and multiverse processes all rely on physics at energy scales far beyond current experimentation. Confirming or refuting these models would not only illuminate the universe's past and future, but also advance our understanding of the most fundamental laws of reality. Importantly, the concept of recurrence does not imply inevitability. Different models produce different predictions, and the universe's ultimate trajectory depends on factors we are only beginning to understand: the true nature of dark energy, the behavior of gravity under extreme conditions, and the role of quantum phenomena at cosmological scales. While scientific inquiry may one day provide greater clarity, the future of the cosmos remains an open and tantalizing frontier. Ultimately, the question of whether another Big Bang could occur exemplifies the essence of cosmology, the interplay of evidence, theory, and imagination. It reminds us that the universe is not static, but a dynamic, evolving entity. Even as we map galaxies, measure cosmic expansion, and probe the earliest moments of time, we glimpse only a portion of reality. The potential for recurrence encourages continued exploration, inspiring humanity to seek deeper understanding while embracing the mystery that surrounds us. In conclusion, while current observations favor a one-way expansion, theoretical models suggest that the universe may be capable of renewal, whether through cyclic evolution, quantum bounces, or multiversal creation. These possibilities expand our conception of reality, blending scientific rigor with philosophical wonder, and offering a vision of the cosmos that is endlessly fascinating, dynamic, and profound. The human fascination with the cosmos stretches back thousands of years. From ancient stargazers charting the motions of planets to modern cosmologists analyzing the cosmic microwave background, humanity has always sought to understand its place in the universe. The study of cosmic origins, from the Big Bang to the possibility of recurrence, is more than a scientific endeavor. It is a profound philosophical pursuit, a reflection of our innate curiosity and desire for meaning. Cosmology confronts questions that touch the very essence of existence. What does it mean for something to begin? If time itself emerged from the Big Bang, can we even speak of it before? How does the vast scale and age of the universe influence our perception of life, purpose, and mortality? These questions bridge science and philosophy, showing that understanding the universe is as much an intellectual and existential journey as it is an empirical one. One of the most striking philosophical implications arises from the sheer scale and age of the universe. With over 13.8 billion years of cosmic history and billions of galaxies, each containing countless stars and planets, humanity occupies a tiny yet conscious corner of existence. This perspective fosters both humility and awe. On the one hand, we are infinitesimal in the cosmic panorama. On the other, our ability to comprehend the universe, to detect relic radiation from the early cosmos, to map galaxies billions of light-years away, is extraordinary. This duality fuels reflection on human significance, small in scale, yet capable of remarkable insight. The search for origins also intersects with questions of meaning and causality. If the universe began in a singular event, what does that imply about purpose or design? If cyclic models or multiverse scenarios hold true, Does recurrence suggest an eternal rhythm, or does it challenge the notion of a singular, intentional creation? Philosophy and cosmology converge here, using scientific reasoning to explore questions traditionally addressed through metaphysics, theology, or existential inquiry. The concept of time is another philosophical frontier revealed by cosmology. In classical experience, time flows linearly from past to future. Yet models of the Big Bang, cosmic inflation, and quantum bounces suggest that time may be more complex. The universe may possess regions where time behaves differently. Or it may be emergent, arising from more fundamental physical processes. These ideas force a re-examination of human assumptions about causality, continuity, and the nature of reality itself. Human curiosity also drives the philosophy of knowledge and epistemology. How can we know the universe's earliest moments when they are beyond direct observation? Cosmologists rely on indirect evidence, theoretical models, and careful reasoning. This interplay between observable facts and imaginative inference highlights a profound philosophical point. Understanding reality requires both empirical rigor and creative thought. Science, in this sense, becomes a bridge between human cognition and the cosmos. A disciplined yet imaginative exploration of existence, the contemplation of a possible recurring preparing. Big Bang or multiverse further challenges conventional notions of uniqueness and finality. If the universe is cyclic, or if countless universes exist simultaneously, traditional concepts of creation, end, and singularity are replaced by continuity, multiplicity, and infinite possibility. Philosophically, this expands our imagination and reshapes our understanding of existence, inviting reflection on themes of eternity, change, and cosmic rhythm. Ultimately, the study of cosmic origins is a mirror reflecting humanity itself. Our desire to comprehend the universe reveals a profound feature of our species, the drive to seek understanding, to ask questions that may have no definitive answers, and to find wonder in the unknown. Philosophical reflection and scientific exploration are intertwined, each enriching the other, allowing humans to engage with the cosmos both intellectually and emotionally. In the next section, we will explore how philosophical reflections intersect with scientific inquiry, and how contemplating cosmic origins shapes ethics, meaning, and the human worldview. The quest to understand the universe is a collaboration between science and philosophy, each informing and challenging the other. While science provides empirical tools, models, and observations, philosophy encourages reflection on meaning, interpretation, and the limits of knowledge. Together, they create a richer understanding of cosmic origins and humanity's place within the cosmos, one area where science and philosophy converges in exploring the concept of time. Cosmological models of the Big Bang, cosmic inflation, and quantum bounces challenge the intuitive, linear notion of time. Philosophers consider whether time is fundamental or emergent, whether it exists independently of the universe, or whether it is a property arising from physical processes. These questions intersect directly with scientific exploration, as physicists develop models in which time may be cyclical, emergent, or even relative across different regions of spacetime. By combining rigorous analysis with philosophical inquiry, humans attempt to reconcile observation with intuition, grounding speculation in reasoned understanding. The nature of existence is another philosophical dimension illuminated by cosmology. If the universe originated from a singular event, or if multiple universes emerge through eternal inflation, traditional concepts of causality and creation are re-examined. Philosophers ask, what does it mean for something to exist out of nothing? What is the role of potentiality, possibility, and necessity in shaping reality? These questions find partial answers in scientific models, which explore how space, time, and energy behave under extreme conditions. The dialogue between philosophy and science allows for nuanced reflection. Evidence informs thought, and thought expands the scope of inquiry. Human ethics and perspective are also influenced by cosmological understanding. Recognizing the vastness of the universe, the impermanence of stars, and the fragility of life encourages humility and stewardship. Philosophy invites reflection on our responsibility within the cosmic context. How should intelligent beings relate to a universe that is vast, indifferent, yet comprehensible? Scientific discovery, revealing the interconnectedness of cosmic processes and the delicate balance sustaining life, reinforces ethical contemplation. Together, science and philosophy foster a worldview that is both aware of human limitations and inspired by human potential. The concept of uncertainty and limitation is central to both fields. Cosmologists acknowledge that certain aspects of the universe, such as pre-Big Bang conditions or the ultimate fate of the cosmos, may remain forever beyond direct observation. Philosophy complements this by exploring how humans reason in the face of uncertainty, how meaning can be derived from partial knowledge, and how imagination and curiosity drive inquiry. This synergy between empirical rigor and reflective thought exemplifies the human approach to understanding the cosmos. A balance of evidence, creativity, and humility. Furthermore, contemplating recurring universes or multiverses reshapes human notions of significance and purpose. If countless universes exist, each with its own Big Bang-like events, our existence becomes part of a vast, ongoing cosmic process. This perspective challenges anthropocentric assumptions while enriching philosophical reflection. It encourages humans to see themselves as participants in an extraordinary, dynamic reality, capable of observation, reasoning, and appreciation of cosmic patterns. Ultimately, the dialogue between science and philosophy demonstrates that understanding the universe is not merely a technical endeavor. It is an intellectual and emotional journey, a merging of observation, theory, and reflection. Through this dialogue, humans cultivate insight into the mechanics of the cosmos, the nature of existence, and the meaning of our own fleeting yet conscious lives within the universe's vast expanse. In the next section, we will explore the personal and existential implications of cosmic reflection, considering how contemplating origins, the Big Bang, and potential recurrence influences human worldview, creativity, and philosophical inquiry. Reflecting on the origins of the universe inevitably shapes our personal and existential understanding. The immense scale of cosmic time and space, billions of light years across, billions of years deep, forces a reevaluation of human concerns and priorities. In the context of the universe's vastness, daily struggles and achievements are seen through a broader lens, fostering humility, awe, and a profound sense of wonder. Contemplating the Big Bang and the possibility of recurring universes encourages humans to confront questions of purpose, significance, and continuity. Are we a fleeting anomaly, or do our conscious experiences hold meaning in a larger cosmic narrative? Even in scenarios where the universe undergoes cycles or infinite births of new universes, our awareness allows us to reflect on existence in a unique way. Philosophy teaches that meaning is not necessarily dictated by cosmic scale. Instead, significance can arise from conscious experience, creativity, and the pursuit of knowledge. Cosmic reflection also inspires creativity and imagination. Artists, writers, and thinkers throughout history have drawn upon the mysteries of the universe to explore abstract ideas, create profound narratives, and express awe. The possibility of multiple universes, cyclic Big Bangs, and quantum phenomena stimulates imagination, encouraging humans to think beyond the confines of immediate perception. Science informs this creativity, while philosophy provides the conceptual frameworks to interpret and integrate these ideas into a meaningful worldview. Existentially, contemplating the universe reinforces resilience and curiosity. Awareness of cosmic impermanence, the inevitable death of stars, galaxies, And eventually, the universe itself can be both humbling and motivating. Human lives are brief against the backdrop of cosmic time, yet this brevity imbues existence with urgency and significance. Our capacity to study the cosmos, ask profound questions, and seek understanding highlights the remarkable cognitive and imaginative abilities of our species. The study of cosmic origins also fosters intellectual humility and openness. Scientists and philosophers alike acknowledge the limits of current knowledge, the true nature of dark energy. The conditions preceding the Big Bang and the ultimate fate of the universe remain uncertain. Embracing these uncertainties encourages a mindset that values inquiry over dogma, curiosity over complacency, and exploration over assumptions. This attitude extends beyond cosmology, influencing how humans approach knowledge, ethics, and understanding in all domains of life. Finally, contemplating the universe invites a sense of connection. Though humans are minuscule in scale, the very act of observing, theorizing, and reflecting establishes a profound link between consciousness and the cosmos. We are not separate from the universe. We are participants in its unfolding story. Each discovery, each reflection, is a dialogue with the cosmos itself, a recognition that human curiosity is not merely an individual trait, but a fundamental aspect of existence's ongoing narrative. In conclusion, the philosophical reflections inspired by the Big Bang, cosmic origins, and the possibility of recurrence shape both our understanding of the universe and our human experience. They encourage humility, wonder, creativity, resilience, and connection, offering a framework for engaging with existence in a meaningful way. By combining scientific insight with philosophical reflection, humanity cultivates a richer appreciation of reality, embracing mystery, uncertainty, and the endless potential of the cosmos. As humans, our awareness of the universe transforms how we perceive ourselves. Understanding cosmic origins from the Big Bang to the evolution of galaxies, stars, and planets places humanity within a vast, interconnected web of matter and energy. We are both insignificant in scale and remarkable in consciousness, capable of observing phenomena billions of light years away, detecting relic radiation from the earliest moments of time, and theorizing about the conditions before the Big Bang. This duality, small in scale, but capable of profound understanding, encourages humility and wonder. When considering the billions of galaxies, each containing billions of stars, our planet becomes a tiny stage upon which life briefly emerges. Yet within this tiny stage, consciousness arises, curiosity flourishes, and meaning is created. Humans are not separate from the cosmos. We are expressions of the same fundamental processes that forged stars, planets, and cosmic structures. Cosmic awareness reshapes our understanding of time and history. The universe's 13.8 billion-year journey contextualizes human history, revealing our civilization as a fleeting yet remarkable episode. From the formation of atoms in the cores of ancient stars to the assembly of galaxies, the processes that led to our existence unfold over incomprehensible timescales. Recognizing this cosmic timeline invites reflection on the fragility of life, the brevity of human experience, and the preciousness of knowledge. Our understanding of the universe also fosters a sense of connection and unity. While our planet may seem isolated in the vastness of space, the same physical laws govern distant galaxies, black holes, and emerging stars. Humanity is woven into a universal story that transcends borders, cultures, and generations. This cosmic perspective can inspire cooperation, empathy, and a shared sense of responsibility for life on Earth. Furthermore, contemplating the universe encourages intellectual curiosity and exploration. The Big Bang, cosmic inflation, and the potential recurrence of universes challenge humans to extend inquiry beyond immediate experience. Each discovery, from the detection of gravitational waves to mapping the cosmic microwave, background reveals layers of reality previously unimaginable. This pursuit of knowledge demonstrates humanity's unique capacity to bridge imagination and observation, transforming wonder into insight. The study of cosmic origins also shapes ethical reflection, understanding the fragility of life, the rarity of habitable worlds, and the potential finitude of cosmic structures can inspire stewardship of the Earth and responsible use of technology. Humanity's place in the cosmos is not only observational, but participatory. Our choices influence the survival, flourishing, and legacy of life. This cosmic responsibility grounds ethical thought in the context of universal processes. Finally, the human perspective on the cosmos emphasizes creativity, art, and meaning-making. Philosophers, writers, and artists have long drawn inspiration from the stars, imagining worlds beyond our own, reflecting on time, and exploring existential themes. Scientific understanding amplifies this creativity, providing structure, evidence, and new horizons for exploration. The universe becomes a canvas, and human curiosity transforms observation into narrative, reflection, and beauty. In the next section, we will explore how humanity's technological and scientific endeavors extend our cosmic presence, considering space exploration, interstellar ambition, and the future of human understanding as we continue to reach beyond our planetary home. Asterisk. Humanity's curiosity about the universe has driven technological and scientific achievements that extend our reach far beyond Earth. From early astronomical observations with telescopes to interplanetary missions, our species has sought to understand and interact with the cosmos, transforming abstract wonder into tangible knowledge. One of the most transformative tools has been telescopic observation. From Galileo's first telescope to modern space observatories like Hubble and the James Webb Space Telescope, humans have expanded their sensory horizon, observing galaxies billions of light-years away, detecting exoplanets, and capturing the faint glow of the early universe. These instruments allow us to probe the universe's history, verify theoretical models like cosmic inflation, and explore the conditions that gave rise to stars, planets, and life. In doing so, humans actively participate in the cosmos, converting light from distant events into understanding and insight. Space exploration missions further extend humanity's reach. Robotic explorers such as the Voyager probes, Mars rovers, and deep space observatories have provided unprecedented data on planetary atmospheres, magnetic fields, and cosmic radiation. These missions offer a direct connection to worlds beyond Earth, informing theories about planetary formation, the potential for life elsewhere, and the physical processes governing our solar system. They exemplify humanity's ability to turn curiosity into tangible presence and interaction with the universe. In addition, advancements in physics and cosmology allow humans to simulate cosmic events, from star formation to black hole collisions, offering insight into phenomena impossible to observe directly. Theoretical models, combined with computational power, permit the study of the universe's origins, evolution, and potential futures. Through mathematics and simulation, humans effectively create virtual laboratories, exploring the Big Bang, cosmic inflation, and the physics of potential multiverses. This integration of observation and theory highlights the uniquely human capacity to imagine, test, and understand the cosmos. Interstellar ambition also shapes our perspective. Projects aimed at sending probes to nearby stars, studying exoplanets, and even considering human habitation beyond Earth reflect an aspiration to become active participants in the cosmic story. While technological and logistical challenges remain immense, these efforts demonstrate humanity's drive to extend existence, knowledge, and influence across space. By envisioning a future in which humans may travel to distant worlds, we embrace a role not just as observers, but as explorers and stewards of the cosmos. The pursuit of cosmic knowledge also inspires, Innovation on Earth. Technologies developed for astronomy. Spacecraft and planetary observation often lead to advances in computing, materials, science, and communication systems. These innovations reinforce the idea that engagement with the cosmos has practical, transformative effects, linking curiosity and exploration to everyday human life. Finally, the interplay of science, exploration, and imagination fosters a collective sense of identity and purpose. Recognizing that we are part of a vast, dynamic universe encourages collaboration across nations, disciplines, and generations. It nurtures a shared vision to understand, preserve, and participate responsibly in the unfolding story of existence. Cosmic exploration becomes a reflection of human aspiration, resilience, and the relentless pursuit of knowledge. In the final section of Part 10, we will explore the philosophical, emotional, and meditative aspects of humanity's place in the cosmos, providing a reflective conclusion that ties together the journey from the Big Bang to the present and beyond. As we conclude this journey through the cosmos, from the mysteries preceding the Big Bang to the potential for recurring universes, it becomes clear that humanity occupies a unique position in the grand tapestry of existence. We are observers and participants, tiny yet conscious entities capable of grasping concepts that span billions of years and trillions of miles. This duality, our minuteness in scale, coupled with the vastness of our awareness, mites both humility and wonder. Meditating on our cosmic context encourages a sense of connection across time and space. The atoms composing our bodies were forged in the hearts of ancient stars, remnants of explosions that seeded the universe with the building blocks of life. Every breath, every heartbeat is a subtle echo of cosmic processes that predate humanity by billions of years. Recognizing this continuity fosters reverence. Life is both transient and eternal, fleeting in individual experience, yet persistent in the grand cosmic cycle. Our awareness of the universe's vastness and complexity also inspires contemplation of meaning. In a cosmos indifferent to human existence, significance arises not from scale or permanence, but from consciousness itself. Our ability to reflect, create, and explore infuses the universe with meaning, however ephemeral. Philosophers, scientists, and artists alike remind us that understanding the cosmos is more than knowledge acquisition. It is a participatory act, an engagement with reality that shapes our values, purpose, and imagination. The potential for future Big Bangs or multiversal cycles further deepens this reflection. If universes arise and fade in a vast ongoing process, then existence is a symphony of beginnings and endings, a dance of matter, energy, and consciousness. Humanity's role is to observe, understand, and appreciate this rhythm. Even in the face of uncertainty, the act of inquiry itself connects us to the universe, making our lives part of a continuum that transcends individual perception. Cosmic meditation also highlights our responsibility and stewardship. Understanding the fragility of life and the finite nature of planetary systems encourages care, empathy, and foresight. The universe may continue with or without us, yet our conscious presence allows us to act with intention, to preserve knowledge, life, and culture, and to extend humanity's legacy across time and space. Awareness of cosmic processes is thus not merely intellectual, but ethical, shaping choices in alignment with the broader flow of existence. Finally, reflecting on humanity's place in the cosmos evokes a profound sense of awe and inspiration. We are participants in an extraordinary story, witnesses to the unfolding of time, matter, and energy on unimaginable scales. The mysteries of pre-Big Bang physics, cosmic inflation, and the potential recurrence of universes remind us that reality is vast, dynamic, and full of wonder. Our capacity to explore, imagine, and reflect is itself a remarkable aspect of this universe, a testament to the extraordinary potential of conscious life. As this journey concludes, The listener is invited to rest in the meditation of cosmic scale, to hear the echoes of the Big Bang in the background of thought, to feel the vastness of space as a reminder of humility and possibility, and to recognize that, in contemplating the universe, we also contemplate ourselves, our origins, our existence, and the boundless potential of human curiosity. The cosmos, in all its complexity and mystery, continues to unfold, and humanity, through observation, reflection, and imagination, remains an integral part of this grand, ongoing narrative. In the silence between stars, in the lingering glow of ancient galaxies, and in the quantum whispers of cosmic beginnings, we find a mirror for our own consciousness, and a reminder that the journey of understanding is endless, profound, and deeply human. The future of cosmology is as vast and mysterious as the universe itself. While humanity has made tremendous strides in understanding cosmic origins, the next decades promise unprecedented opportunities to expand knowledge, refine models, and explore previously inaccessible phenomena. Emerging technologies and innovative scientific methods will serve as the foundation for this next wave of cosmic discovery. One of the most promising areas is next-generation telescopes and observational platforms. Telescopes such as the James Webb Space Telescope (JWST) have already transformed our understanding of early galaxies and star formation. Future instruments, including ground-based extremely large telescopes, ELTs, and space-based observatories, will provide even greater resolution, sensitivity, and coverage. These tools will enable the detection of fainter, more distant objects, probing the universe closer to its origin and potentially revealing new insights into cosmic inflation, dark matter, and dark energy. Gravitational wave astronomy is another revolutionary frontier. Since the first detection of gravitational waves in 2015, humanity has gained a new sense of the universe, observing cosmic events invisible to traditional telescopes. Collisions of black holes and neutron stars produce ripples in space-time, offering information about extreme physics, the evolution of massive stars, and the fundamental nature of gravity itself. Future gravitational wave detectors will extend our reach further into the early universe, providing a novel way to observe phenomena that occurred shortly after the Big Bang. Advances in computational cosmology and artificial intelligence will also shape the future of discovery. High-performance simulations allow scientists to model the formation of galaxies, the behavior of dark matter, and the dynamics of cosmic structures with unprecedented accuracy. AI and machine learning algorithms can detect patterns, anomalies, and correlations in vast datasets, accelerating discovery and enabling insights that were previously beyond human capability. Together, these tools will transform raw data into understanding, bridging observation and theory in novel ways. The future also involves exploration of exoplanets and the search for life beyond Earth. By studying planets orbiting distant stars, cosmologists and astrobiologists gain context for understanding the conditions necessary for life, the distribution of habitable worlds, and the potential uniqueness or ubiquity of intelligent life. These endeavors link cosmology to one of humanity's deepest questions. Are we alone in the universe? The answers, even partial or indirect, will reshape our philosophical, ethical, and existential frameworks. Quantum technologies and particle physics further extend cosmological insight. Experiments probing the nature of dark matter, dark energy, and the earliest moments of the universe may provide answers to long-standing mysteries. As particle accelerators, detectors, and quantum sensors become more sophisticated, the boundary between the microcosm and macrocosm blurs, revealing the fundamental underpinnings of space, time, and energy. Finally, interdisciplinary collaboration will define the future of cosmology. By combining astronomy, physics, computer science, and philosophy, researchers can approach cosmic questions from multiple angles, Insights from mathematics, philosophy of science, and even art provide new ways of conceptualizing the universe, generating ideas that inspire both rigorous investigation and imaginative exploration. In the next section, we will examine theoretical frontiers and conceptual breakthroughs, including evolving models of cosmic inflation, multiverse theories, and the possibilities of understanding pre-Big Bang conditions. These ideas will shape the intellectual landscape of cosmology in the decades to come. Asterisk, while observational technology expands the limits of what we can see, theoretical cosmology pushes the boundaries of what we can imagine. As we refine our understanding of the universe, scientists develop bold models and hypotheses to explain phenomena that remain mysterious or entirely unobserved. These conceptual frameworks will define the future trajectory of cosmic inquiry. One major frontier is the study of dark matter and dark energy. Despite comprising roughly 95% of the universe's content, these entities remain largely enigmatic. Dark matter, invisible yet influential in galactic formation and rotation, challenges our understanding of gravity and particle physics. Dark energy, driving the accelerated expansion of the universe, raises profound questions about the ultimate fate of cosmic evolution. Theoretical advances combined with upcoming experiments aim to illuminate the nature of these invisible forces, potentially revolutionizing physics and our understanding of existence. The concept of cosmic inflation and multiverse models represents another theoretical horizon. Inflation proposes a rapid, exponential expansion of space immediately after the Big Bang, explaining the universe's large-scale uniformity. Some models suggest that inflation is eternal, giving rise to an infinite number of universes with varying physical constants and laws. Exploring these ideas challenges human intuition, inviting reconsideration of what is possible and redefining the scope of reality. Such theories remain speculative, yet provide a fertile ground for intellectual exploration. Bridging mathematics, physics, and philosophy. Quantum cosmology is also poised to transform understanding. By applying quantum mechanics to the universe as a whole, researchers investigate the interplay of probability, uncertainty, and the structure of space-time at the smallest scales. Concepts such as quantum fluctuations may hold the key to understanding the origin of the universe itself, potentially revealing what came before the Big Bang or whether time and space as we know them are emergent phenomena. Another exciting frontier is the unification of physics. For decades, physicists have sought a single framework to reconcile general relativity, governing gravity and large-scale structures, with quantum mechanics governing the microscopic realm. Success in this area through string theory, loop quantum gravity, or other approaches could provide a comprehensive description of the universe from its birth to its ultimate fate. Such a breakthrough would redefine not only cosmology, but all of physics, offering profound insights into the origin, structure, and evolution of reality. Artificial intelligence and advanced simulations also drive theoretical progress. By modeling universes with varying physical laws, simulating cosmic evolution under different conditions, and testing hypotheses against massive data sets, AI accelerates discovery and generates novel insights. These tools allow theorists to explore scenarios that are otherwise inaccessible, such as universes with alternative constants, multiple dimensions, or exotic particle behaviors. Finally, interdisciplinary thinking is crucial. Philosophical reflection, mathematical innovation, and imaginative reasoning complement empirical observation and simulation. By questioning assumptions, redefining concepts like time and space, and exploring the implications of new models, humanity can anticipate discoveries that may reshape fundamental understanding. The theoretical frontier is thus both a scientific and a conceptual expedition, requiring imagination as much as measurement. In the next section, we will examine the societal and existential implications of future cosmology. including how evolving knowledge may reshape human philosophy, ethics, creativity, and our place in the universe. As cosmology progresses, its discoveries will not only expand our knowledge of the universe, but also profoundly influence how humanity perceives itself. The potential revelations about dark matter, dark energy, multiverses, and pre-Big Bang conditions invite us to reconsider concepts of significance, purpose, and the very nature of reality. Understanding the universe's vastness and complexity fosters humility and perspective. In contemplating phenomena billions of light-years away or forces beyond direct perception, humans recognize the limits of individual experience. This humility can inspire both curiosity and respect for the universe, for life on Earth, and for the interconnected web of matter and energy that links all existence. As cosmology reveals more about the cosmos, our philosophical frameworks may evolve to accommodate scales of time, space, and possibility that were once unimaginable. Future cosmological insights also challenge our concepts of identity and uniqueness. If multiverse theories are confirmed, human existence may be one of countless variations across different universes. Yet, even within a multiverse, our consciousness remains a remarkable expression of cosmic processes. This paradox of relative insignificance in scale versus the uniqueness of conscious awareness can inspire a deeper appreciation of life, creativity, and the act of observation itself. The advancement of cosmology will inevitably influence ethics and responsibility. Recognizing the fragility of life, the scarcity of habitable worlds, and the finite nature of planetary systems may heighten humanity's sense of stewardship. Decisions about technology, environmental preservation, and interstellar exploration will increasingly be informed by a cosmic perspective, aligning ethical considerations with a broader understanding of existence. Humanity may come to see itself not as dominators of Earth, but as participants in a larger, dynamic universe. Moreover, the creative and imaginative potential of humanity will expand alongside scientific discovery. Artists, writers, and philosophers will draw inspiration from emerging cosmological theories, creating narratives, art, and concepts that bridge science and imagination. The interplay between empirical observation and creative interpretation enriches human culture, turning abstract knowledge into meaning, reflection, and emotional resonance. Cosmology's future also promises to redefine education and intellectual aspiration. As tools and data become increasingly sophisticated, learning about the universe may become more immersive, interactive, and interdisciplinary. Students, researchers, and the public will engage with simulations of cosmic evolution, multiversal possibilities, and quantum phenomena, fostering a generation attuned to both analytical reasoning and imaginative thinking. Such education bridges science, philosophy, and wonder, cultivating thinkers capable of grappling with the profound questions of existence. Finally, future cosmology encourages a meditative awareness of existence. By reflecting on the life cycle of stars, the evolution of galaxies, and the potential recurrence of universes, humans are invited to situate themselves in a broader narrative. These contemplations can cultivate serenity, awe, and a deep connection to reality, allowing individuals to embrace uncertainty and appreciate the elegance and mystery of the cosmos. In conclusion, the future of cosmology is not merely a scientific endeavor. It is a human journey. By expanding knowledge, inspiring reflection, and shaping imagination, cosmology will continue to transform our worldview, ethical frameworks, and sense of belonging. As humanity reaches farther into space and deeper into the fabric of reality, we are reminded that understanding the universe is inseparable from understanding ourselves, a pursuit that is endless, profound, and inherently human. As we reach the conclusion of this immersive exploration of the universe from the mysteries preceding the Big Bang to the frontiers of future cosmology, It is time to pause and reflect on the extraordinary journey humanity has undertaken. Our quest to understand the cosmos is not merely scientific. It is deeply philosophical, emotional, and existential. Throughout this journey, we have glimpsed the staggering scales of time and space. From the first instance of cosmic inflation to the birth of galaxies, stars, and planets. Humanity's awareness of this vastness underscores our dual nature, small in scale, yet immense in consciousness. We are both ephemeral and extraordinary, living brief lives within a universe whose complexity stretches beyond comprehension. This tension between minuteness and significance defines the human experience, inspiring awe, humility, and curiosity. Understanding the origins of the universe also illuminates the interconnectedness of all things. The atoms that make up our bodies were forged in the hearts of ancient stars, traveling across cosmic distances before coalescing into planets and life. The processes that shaped galaxies, nebulae, and solar systems ultimately set the stage for consciousness to emerge. In this light, humanity is not separate from the cosmos. We are the universe observing itself, reflecting on its own complexity and beauty. Throughout history, scientific exploration has provided frameworks for interpreting these cosmic mysteries. From the first telescopic observations to the development of the Big Bang Theory and modern cosmological models, humans have continually sought to translate wonder into understanding. Yet, even as knowledge expands, uncertainty remains. Questions about pre-Big Bang conditions, dark matter, dark energy, and potential multiverses persist, reminding us that the universe is both knowable and infinitely mysterious. This balance between discovery and uncertainty is not a limitation, but a source of inspiration. Urging continued inquiry and reflection, contemplating the universe also invites profound philosophical reflection. What does it mean to exist in a cosmos that predates life by billions of years? How should humans understand significance, purpose, and responsibility in a universe so vast and indifferent? The answers are not prescribed by science alone. They emerge from the interplay of observation, imagination, and philosophical contemplation. By engaging with these questions, humans cultivate a deeper appreciation of life, knowledge, and consciousness itself. Our journey also emphasizes the power of curiosity and exploration. Humanity's drive to look beyond immediate experience to observe distant galaxies, measure cosmic radiation, and simulate the early universe demonstrates the unique capacity of consciousness to transform wonder into knowledge. Each discovery not only expands our understanding of the cosmos, but also reinforces our role as participants in its unfolding story. Exploration is both outward, into the depths of space, and inward, into the depths of thought and reflection. Finally, reflecting on this cosmic journey cultivates a sense of awe and meditation. Listening to the echo of the Big Bang, imagining the birth of stars, or contemplating potential future universes evokes emotions that transcend words. It is in this space between knowledge and wonder, observation and imagination that humans find profound meaning, serenity, and connection. The universe becomes not only an object of study, but also a mirror for consciousness, inviting us to reflect on our origins, our existence, and the boundless possibilities of human thought. As the journey through the universe comes to a close, it becomes clear that the human experience is inseparable from the cosmos we study. Observing distant galaxies, contemplating cosmic inflation, and imagining potential multiverses evokes not only intellectual understanding, but profound emotional resonance. The universe inspires awe, humility, and a sense of connection that transcends the limitations of daily life. Cosmology teaches that our origins are entwined with the stars. Every element of our bodies, every breath we take, is part of a vast cosmic cycle that predates humanity by billions of years. This understanding fosters a deep sense of belonging, a realization that we are not passive observers, but participants in a grand unfolding narrative. By reflecting on this continuity, humans gain perspective on life, mortality, and the fleeting yet remarkable nature of existence. The pursuit of knowledge about the cosmos also underscores the value of curiosity and imagination, even as scientific instruments reveal the universe with unprecedented clarity. Human creativity shapes the interpretation, meaning, and cultural impact of these discoveries. Art, philosophy, and storytelling intersect with observation, transforming raw data into insight, reflection, and wonder. In this way, humanity co-creates meaning with the cosmos, translating the incomprehensible into a narrative that resonates emotionally and intellectually. Finally, contemplating the cosmos encourages meditative reflection and serenity. The scale, complexity, and mystery of the universe invite humans to pause, to marvel, and to embrace a sense of humility and gratitude. In moments of quiet reflection, the echo of cosmic origins, the dance of galaxies, and the potential for future universes provide both perspective and inspiration. We are reminded that understanding the universe is not solely an academic pursuit. It is an invitation to experience awe, cultivate wonder, and find meaning in our place within the cosmos. As this journey draws to a close, imagine yourself floating among the stars, drifting through the silent expanse of space. Galaxies swirl in the distance, ancient light streaming across unimaginable distances, carrying with it the story of the universe from its first moments. The Big Bang, cosmic inflation, and the formation of galaxies unfold like a cosmic symphony, an eternal dance in which you, too, are a part in this vastness. Human life may seem fleeting, almost imperceptible, but within each consciousness lies the capacity to understand, to reflect, and to wonder. The atoms of your body were born in stellar furnaces. The rhythms of your existence echo the cycles of stars and galaxies. You are, in essence, a product of the cosmos contemplating itself. This awareness is both humbling and profoundly empowering. Consider the mysteries that remained, the dark matter and dark energy shaping the universe, the possibility of other universes, the ultimate fate of space and time. These questions may never be fully answered, yet the pursuit of knowledge itself is a form of participation in the cosmic story. Every thought, every discovery, every moment of reflection is a thread woven into the tapestry of understanding. Take a deep breath and feel the connection. The universe is not merely around you, it is within you. In your consciousness, your curiosity, your capacity to perceive and dream. Imagine looking back across billions of years of cosmic history and forward into countless possibilities. In this perspective, worries and limitations of daily life fade, replaced by awe, gratitude, and a profound sense of belonging. As the stars continue to burn, galaxies continue to spin, and time stretches endlessly. Remember that humanity's journey is ongoing. The act of observing, learning, and reflecting is itself a bridge between the finite and the infinite. The cosmos invites you to imagine, to question, and to marvel. Even as the universe expands and evolves beyond comprehension, your awareness, your consciousness, and your curiosity are the means by which its story becomes known. In this quiet reflection, allow yourself to rest in the beauty of existence, the mystery of beginnings, and the possibilities of what is yet to come. The universe is vast, eternal, and unknowable in its entirety, but through wonder, contemplation, and imagination, it becomes a shared experience, a living meditation connecting all of humanity to the stars, the galaxies, and the very fabric of reality.